Hi, good morning all. It's top of the hour, so we should probably get started. As a reminder, please keep yourself muted unless you'd like to ask a question. And if you'd like to ask a question, you can either ask it on the chat or you can turn on your camera so that people know that you're interested in asking a question. And then if the speaker could recognize you, then go ahead and ask your question. Before we get started, I'd like to thank all of the sponsors of the Linux Plumbers Conference, including our diamond sponsor, Facebook. And with that, I'd like to introduce Konstantin, who has been doing a lot of amazing work on the infrastructure for kernel.org. And today he's going to speak about lore and B4. So thank you very much.
Thank you, Ted. Just sound check, everything works. Everybody can see me, hear me. It's all good. If not, now's your time to say something. I think I'm supposed to get presenter tools, Ted. So I can do left, right on the slides. Anyway, while we're doing that, just the subject for the topic is about maintaining workflows. Yep, I got it, Ted, thank you. And we are going to discuss what we're doing with lorekernel.org, specifically with tools like B4 and another tool I'm going to mention, which is called LEI or lay. And there's a pun there that I will come to in due time. All right, let's get started. See if I can paginate this. There we go. In the beginning, there was email. By the way, if you want to ask questions, just type it in the chat. It's open right there. I will see it. It's a lot easier than trying to figure out if you're unmuted or if your camera is working or anything. As I'm going along, ask the question in the chat. I will periodically make sure to look over there and see if there's a question. All right, so starting off. In the beginning, there was email. As everybody knows, about 30 years ago, Linus sent an email, or rather a Usenet post to a news group saying that he's starting this little project that is totally not professional or anything like that. And everybody enjoyed using email, sending an email to news groups, receiving them in the mailing list, and everything was good. And that's the end of my presentation. Thank you very much for coming. I'll be here all week, literally. All right. Anyway. Joke one, off the list, check mark. All right, RFC 2822 is actually the standard. There's actually a newer standard, but everybody's used to seeing it called RFC 2822. It's the standard that describes the format of the message, not specifically the protocol over which the message is delivered. So Usenet works with RFC 2822 messages, of course. This was the lists before the lists. The email existed alongside, but everybody who needed to share communication over a large group of people used Usenet. It was nice, but and it was decentralized. It started out at Duke University, where I worked for quite some time. So this is like a shout out to my old workplace. It didn't really deal well with abuse because of its decentralized nature. It was really hard to monitor who is allowed to post messages, who is not allowed to post messages. So after a little while, Usenet just turned into something that is either illegal or spam or both, or anyway. So everybody jumped ship to mailing lists, which is what Linux kernel development community did, or the web boards, which is also something that happened in the past. Unfortunately, abuse has since intensified. It didn't really solve anything. There was continued centralization for the mailing lists and for especially for web boards. And there are certain important downsides to web boards. Spam continued on web boards, so it didn't really solve a problem there. We just needed larger and larger anti-spam protection mechanisms. We started introducing things like SPF for email and DKIM for email and DMARC for email. And unfortunately, what ended up happening is that it broke delivery from many, many mailing lists, which is not really the fault of DKIM. It's the fault of how we used to do mailing lists. If you've ever set up a mailing list, you know that there's an option to add the little thing to the subject and the little thing to the footer. And it would do things like strip attachments and everything like that. Unfortunately, all of these nice and little neat measures ended up breaking DMARC and specifically DKIM signatures. So it's actually easy to do both DMARC and lists. I have a little discussion on how best to do it. You can go ahead and do it. You click on that link in the PDF file if you want to download it, or just Google DMARC and mailing lists. They're not mutually exclusive. It's a myth that they are. You can actually set up a mailing list that as long as the message is a DKIM signed, that is perfectly DMARC valid. So, and as I mentioned, RFC 2822 is actually not protocol specific. Messages do not need to arrive via SMTP. And we'll discuss other alternatives in the next future. So why are we still using email, right? Well, if you think about it, email remains the only standard, interoperable, widely used point-to-point messaging system. The only thing that came kind of close to this was XMPP, and it's kind of slowly dying at this time because every major vendor has killed support for XMPP. It is decentralized, as I mentioned. It is also importantly vendor neutral. If you're working at Google and you need to communicate with somebody at Microsoft, you can send an email from Google to Microsoft and you can expect it to arrive. It may get mangled. It can get quarantined if you did something strange or the SMTP gateway didn't like it. But most of the time, an email that you send from one vendor to another vendor gets accepted, processed, and shows up in the inbox. It also provides full address portability. This is assuming that you use your own domain. For example, my own domain, I switched at least 4 or 5 different providers, preserving my own domain name and my own email address. If I didn't like one, I can always move to a different one. There's no sort of penalties for doing that. You can do it as often as you like. So this gives you the freedom to do so. You can host on your own as well. Importantly, email, since the DKIM introduction, provides strong domain level attestations. There are signatures, cryptographic signatures that's part of the headers that allow you to verify that an email was sent from a specific domain, that it passed their signing protocols, that before it left the specific vendor, that the message was signed with their cryptographic signature. You can download it, you can verify it. As long as the domain record continues to exist, you can continue doing so for anytime in the future. And also, importantly, we kind of managed to handle abuse with introduction of DKIM and DMARC. It's not great. You still receive a lot of spam, but what continues to happen is that it's not really the fault of email, it's just the fault of any system that receives enough eyeballs will get abused this way. We've seen this happening to every other mechanism, every other communication platform out there. I've had, Facebook, I've had Telegram, anything, I receive spam on all of them. So it's not really something that is just specific to email. And email is actually more problematic to protect, primarily because it is decentralized. There's no one place where you can filter out all of the accounts, filter out all of the spammers. Another interesting part of email is that it allows for mixed messages. And this is not, I don't mean a double entendre. I mean that there's multiple parts in the MIME standard. You can say this part is for humans. This part is dedicated for robots. This is an attachment file that you don't have to render. You can just let the human download it. This is useful if, for example, you want to say, this is a notification for you. This is what this notification is about. If you want to process this notification, there is a part that's specifically aimed at your processing engine that you can feed this message to, and the processor will know what to do with that. And an important part of this is that this is what all the kernel developers will tell you, is that everything is in one place. This is important. One of the downsides of the web boards is that if you ever had a situation where you posted something on the internet and multiple news websites had a piece about it, you would then go to all of these news websites to check the comments to see if you need to comment there. In the Hacker News, they maybe need to comment something. And LWN, did the register post something in the comment? Usually you ignore the comments and register anyway, so I'll forget that example. But this is a problem that you would have to go and check multiple sources on the internet to see if you need to respond to something, or you need to correct somebody's misconceptions about your work and so forth. As opposed to everything just arrives in your inbox, right? If there is a notification, you don't need to just click and link. Everything is right there. You can just reply in line, and you don't need to create an account anywhere. You don't need to, navigate through a weird system of comments that they might have, or so forth. This is why email still rules for a lot of the stuff that we have to do. As I mentioned, the problem with having multiple different systems where you have to go and check things is that maintainers don't scale. And there is what I call the death by 10,000 shortcuts. Once you learn shortcut to do something very efficiently, very quickly, it is extremely difficult to unlearn that and to learn something new and totally different. Or it is even more difficult to have multiple sort of namespaces for, if I'm on this site, this is the set of shortcuts I have to use. If I'm on this site, this is a different set of shortcuts I have to use. For example, if you're a Gerrit user, then you have to have a certain set of shortcuts. You sort of have to remember. If you're going then to GitHub, it's a totally different set of shortcuts. If you're then on Gmail, it's again a different set of shortcuts. Our brains don't really work that way. One of my biggest problems is that if I need to copy paste something from a terminal or from a website to the terminal, of course, it's Control-Shift-C, and the website is Control-C, and half the time I just open developer tools because I clicked the wrong shortcut. The example is Linus maintains micro Emacs because of what he calls muscle memory. He learned a set of shortcuts back when he was a student in Finland, and micro Emacs worked with Finnish, one of the best tools back at the time, and so he still has trouble relearning the set of shortcuts to work with any other tool. So he continues to maintain and use micro Emacs, even though he's probably the only user in the world at this time. There's obligatory XKCD reference. You probably saw that one. It's about the guy who refuses to join the interplanetary cloud of conscience because he just likes his IRC interface. We all have been there. So we want maintainers to focus on maintaining and not remembering which shortcuts they should use on which website. And if something is working well for a maintainer, our goal is to avoid breaking it. I call this don't break maintainer flow, kind of like don't break user space is the mantra for the Linux kernel. I try to stick to don't break maintainer flow for the past 10 years that I've been doing the same thing. Sometimes it is inevitable because a tool may just stop being supported, or it is costing us way too much money to support this specific workflow for one person that may be using it that may be able to switch to something else with relative ease. Fairly recently, I shut down Patchwork for LKML, which nobody really was using except maybe one or two people, and I hopefully was able to provide them with alternatives. There was one time when I turned off, you used to be able to definger kernel.org and receive the status of the latest kernel releases. I turned that off as one of the first things when I first started kernel.org, and oh my God, I received complaints about it for the 3-4 years after that. Why? What I'm trying to say is that mail user agent, I used to say mutt everywhere because I assume everybody uses mutt, but it's not true. So when you see MUA, just assume it says mutt because in my head it does. So MUA workflows allow maintainers to scale. What they're able to do is they have a set of shortcuts. They have a set of workflows that they're used to that are extremely efficient at grabbing patches, replying to conversations, reviewing code. And they're really good at this. And for them to learn something else takes time and effort, an effort that they would otherwise be spending on actually making Linux better or applying the patches that developers have sent. All right, any questions at this time? None so far. This was kind of an introduction, and I'm going to lean into actual tooling that we built around this. All right, so patches sent via email. Patches are conversations, if you think about that, right? When you receive a patch, it's got everything that is a conversation. If somebody approached you at a conference and started talking to you, say, hey, my name is Alex Eagerdev. I have a suggestion that you have a cool feature. So this is how you do it now. I think you should do it this way. And if you look at the patch, this is literally exactly what it is, right? It says a from. It's got a subject of the conversation. It's got a date when the conversation happened. It's got a commit message, which is the explanation of what you're trying to do and what the results that you're trying to achieve. And it's got the actual patch. And the patch is, of course, showing you this is your current code, and this is what I suggest your code should be. And this is extremely efficient for a maintainer to look through it because they know the code, they know exactly where this code lives. And it's easy for them to just do a reply all, and just to go line by line or paragraph by paragraph and say, yeah, this is good. I don't think you should be doing it this way. I think you should be doing it better, or our coding standards are slightly different. Please change it this way. And the interleaved email replies that everybody uses are our natural way of doing that. It's very extremely efficient for somebody to do it in their email client, much more efficient than go into a website, finding this line of code and making comments there. This is what I've heard from multiple kernel developers in the past. And it is a great workflow for code reviews. Unfortunately, it's not so great for literally anything else that happens after the code review is complete, right? This is what I call the old maintainer workflow, right? Once you're done with the code review and you want to actually apply the patches that you've received to a Git tree, you would save the submission as an inbox file from your Avail user agent, or you would use a tool like Quilt if you're doing this been doing it for a while. If it's an inbox, it may not save the patches in the right order. You would have to like literally manually change the patch 1 goes here, patch 2 out of 10 goes here, and this is extremely bothersome to do it, but you almost always have to do it with an inbox because they could have arrived at any order really. Then if there's somebody send a follow-up saying, yeah, I reviewed this or I tested this, you have to manually go through all of the replies and say, this is an EC by, this is reviewed by, this is tested by so-and-so. Then you make a Git branch, apply the inbox file, merge into your main branch, and then provide as much relevant info as possible in the actual merge message. Linux complains about it a lot when you just have a useless merge message. You should pay attention to this. Then you send it to an upstream maintainer. Either that's Linus if you're sending pull requests directly to him, or your upstream maintainer to pull your request. And of course, the problem that eventually became blindingly obvious is that we needed good email archives to do this, specifically for the decision crumb trail, right? When you copy pasted the reviewed by and tested by and act by, there was, other than your inbox and the outbox of the person who sent those, there's no confirmation saying that this person actually did this, that you didn't just come up with this on your own. This was kind of the honor code between maintainers to make sure that when you put that in, that you didn't just make that up, right? So email archives, good email archives, allowed us to make sure that everything that goes into the commit message, all of the sign-offs and all of the decisions, we can actually trace them and figure this out. This is public information, publicly available on a public archive site. And before, about 3 years ago, I think, we used gmain.org, which was great. There was lkml.org, which was less great because it's just the Linux kernel mailing list, which is not actually used by anybody really specifically. I think almost everybody CCs it, but almost nobody really pays attention to it because it's just like a fire hose. So what we needed, and this was becoming more and more obvious, especially after the gmain.org had a meltdown and went offline for a couple of months. lkml.org kept having outages and not accessible. But we needed distributed archives, and also the archives that are also continuously updated and replicated. And distributable part was important because we didn't want to be kind of the central site where everything is checked, right? If we are down, then we're back to the similar problem of, well, kernel.org is down, where do I get my information? So we looked at public inbox. Public inbox has some really cool features in it. One, it has a clonable backend. All of the archives that it stores are actually Git repositories themselves. You can clone the entirety of lorekernel.org and have the full copy of it locally, and you can actually set up a full mirror of lorekernel.org on your own. It has, in addition to Git repositories, it indexes all the messages in the Git repositories and provides fast search capabilities on the HTTPS front end. It uses Zapier for that, which is a public, which is open source project, free software project. In addition to just providing good search results, it is also extremely developer-friendly search results. You can have prefixes that specifically are aimed at patch workflows. For example, if you have DFN, that matches the file names from diffs. For example, if you want to go to lowerkernel.org/all and look for DFN maintainers, you can find all the patches that modify the maintainers file. DFHH, it looks for hunk header context, right? This is what, when you say git diff, and it will provide the @ and the function name. This you can look for all of the patches that actually modify your favorite function. Like in this example, I have apeg bus freak is known, just randomly one I picked. You can even find, for example, give me a patch that changed this file to be the following hash. There's a df post search for that. Like I mentioned, lowerkernel.org can be mirrored in its entirety. In fact, with the recent iteration, lowerkernel.org is actually 3 geo-distributed mirror nodes. It's not the main source of data. It mirrors it from our backend system. It is 100% free software. Anyone, and I want to stress this, anyone at any time can set up a full clone and keep it updated. Documentation is, as always, lacking a little bit. I'll try to provide complete docs on how you would be able to do that, but it is actually easy to do and easy to set up. So if you're working from a large company that uses the archival features all the time, or you just want to just set it up on your own because you're interested in doing something like this, or if you're digging for fossils in the archival record, I suggest instead of querying lowerkernel.org directly, that you go ahead and set up a local copy. It's easy to do. Now, it started out as just an archival collection site, but what we soon realized is that it allows for greater workflow automation on top of that. And this is where the tool came, I came up with a tool called B4. And the name is a Star Trek reference. I blame V'ger for this. V'gerKernel.org is the main mailing list site, right? Then lore, of course, is a brother of data, which is a Star Trek reference, and B4 is a prototype Android that was before data and lore. And this is actually a terrible name because when you're searching for B4, it's a valid hex code, so all of the hex dumps also match. This is I kick myself every time when I actually have tried to find something that's related to B4. Mea culpa, unfortunately, it's too late to change that at this point. Now you can install it fairly easily from PyPI. It's written in Python. It's if you don't like PyPI, you can clone the repo and just run pip install requirements.txt. There's only a few requirements that are even not required. It will pull in things like DK invalidation and some of the cryptographic attestation libraries, but you can absolutely run it without them. So you can just clone it from Git. It's on gitkernel.org. You can find it there. And you can probably install it from your distro too, but it's probably got an older version. And it seemed quite wide adoption by maintainers. I'm trying to be humble here, but I think a lot of maintainers are using it right now, and it saves them a lot of time and effort. I'm going to go through some of the major features. Probably most of you already know about them, so I don't want to spend too much time talking about this. B4 Mbox allows to grab whole threads from lowerkernel.org, right? And the threads, what is important, are aggregated from across all lists. They're not just from one specific list. So the cool thing about it is when, for example, you get CC'd, your list, the list that you're monitoring gets CC'd in the middle of a discussion, so that if you wanted to see the entire context of this discussion before what actually happened, before it got CC'd, you can look for that message ID on lowerkernel.org/all, and you can grab the entire thread. And B4 Mbox can add threads to an existing mailbox. So that command, for example, right there, B4 Mbox FO mail, assuming your mail is where your mail dir is, can download the entire thread, filter out the dupes that you already have, and add them to your mailbox. And there's a macro index 4. That's the command you can add to B4 to your MUT RC, for example, so that if you come to a thread that you're missing context on, you can just hit 4. This will grab the entire thread from lowerkernel.org archive and add it to your inbox. This is, like I said, great feature that I use all the time, actually. Now, before AM is probably what is most known to maintainers. It's a workhorse. It gets the thread like a before inbox does, but then it processes it by looking for any follow-up trailers like received by, act by, tested by, and so forth. It will add them to the patch that was actually sent. It will also check DKIM signatures if the library is present. It will check for crypto attestations that we'll talk about in a moment. It will make an mbox file or a maildir file that you can pass to Git AM to actually apply the patch in its ready form to your Git tree. Now, it doesn't, what people don't realize, it doesn't need to use lore.kernel.org. By default, it will go out and get stuff from lore. But if you pass the -m, you can look in your local inbox to get everything from your local source. So if you're offline and you want to be able to use before, you can just, as long as you have everything locally, you can use it without the online presence. That's important. Yeah, just look at before am --help. There's a bunch of commands there. Some of them are lesser known features that I think are cool. So I'm going to mention them here. The -g or guest base. You will look at Git index. If you've seen the patch that's made by Git, it shows the indexes of the files that are being modified. So the guest base will try to look in your local tree, as long as you run this from a local tree. It will try to find where in the tree this patch is without conflicts. So this is useful if you want to be able to apply the patch and know that there are not going to be any conflicts. It does not mean that this is where the patch actually belongs. I'd always provide this caveat that sometimes you just don't know if it depends on something in a different file that it doesn't mention, that is a function that it relies on. But if you're only using, if you need to be able to apply this without any conflicts, that's something to look at. The prep three-way, it gets your local tree ready for a three-way patching. I said I don't know actually what this means. This is not exactly true. I know exactly what this means because I actually wrote this feature, but I don't actually use it a lot, so I assume it's useful, and people tell me it's useful, so I mentioned it there. -c is kind of a hack that a lot of people rely on, actually. If you received a patch series, as long as the subject and the author haven't changed, you can check if if you have a v3, maybe there's somebody posted a v4, or the same author posted a v4 or v5. If you patch -c, you can actually try to find the newer version on lore.kernel.org. Now, before diff, I find is cool, but since I'm not a kernel developer, I don't usually have the trees that are required to make this operation. But if you have a v3 and a v4, for example, you can pass a before diff message ID, and it will show you the range diff between v3 and v4. So this kind of keeps contributors honest. When you respond to v3, yeah, make this change, and the author says, yeah, I made this change, doing the git before diff is allows you to verify that what they actually changed is what they say they changed. It keeps contributors honest. It requires that the index objects are present in the tree. We try to recreate them before we run this diff, so we kind of create fake ranges. So there's some cool Git magic happening in the back end. As long as you have all of the initial indexes in your tree, we should be able to make this work. If not, it will just say, unfortunately, I don't have these indexes. If you know from which tree this is, add it as your remote and pull it, and then we'll be able to present this for you. So before PR is if you receive a lot of pull requests, this will help you process them. Before PR message ID will fetch the request into the fetch head. It will actually, something I didn't mention here, it will check if it's already been applied. So if you don't remember if you processed this or not, it will tell, oh, actually, this is already in your tree, so you don't need to do anything about it. This will check the PGP signature on the tag or on the commit, as long as that's in your local PGP keyring. It will give you verified verified checkmark. It will also verify that commit SHA that it mentions in the message actually matches what the commit is in the remote, because I find that sometimes what happens and people say, please pull up to the following SHA, and when you actually pull it, the remote SHA is different from that, so that the remote either didn't get pushed, or it didn't get mirrored yet, or the maintainer also, oh, I forgot to do this, so I'm going to sneak in another commit there. So you will check and say, oh, actually, the remote that you've just pulled is not matching what the SHA says in the message. So that we'll do this verification. One of the cool things I also do, we'll do -- explode. You can turn a pull request into individual commit. So it will turn a pull request into a patch series, basically. It will add all the 2s and CCs from the original pull request. So you can actually, if you pulled something and you don't like something about it, you can turn it into a series of patch requests, of patches, and reply to individual patches. So you don't need to find the place in the code. You can just do usual code review using this mechanism. And as you know, some of you know, I'm working on the GitHub or Git Forge integration using the PR bot. It will soon be offered as automation. I haven't got around to it fully yet because we needed to get newer version of lore kernel that were in place before we could do that. And something that is, I think, seeing a lot of use is the B4QI, which stands for thank you. It automates the thanks. This has been applied responses for maintainers. There's an auto-thankinator gun, which I named maybe because I watched too many Phineas and Ferb episodes with my kids. Again, it will look at all the patches and series you've downloaded with before AM or before PR. It will try to find these series and these pull requests in your local tree. So you have to run this from a local tree. And it will say, well, you've downloaded this series and I can see that you, as your author, has applied them, merged them into your tree. So I'm going to create a .thanks file that is sort of a cookie cutter response to the submitter. You can then do a git send email for the thanks file. I will also eventually add this, so you will be able to send directly from before. All right. Any questions so far? None? All right. Good. My goodness. Maybe it's just so early that people are just not really awake yet. Okay. Before I test. Yes, Ted.
Yeah, just a quick administrative point. Some folks may be having trouble connecting to the chat. There are chat issues which the planning committee is working on, and Constantine, that might be one of the reasons why you're not seeing any questions on the chat. The shared notes is working, so folks could switch to the shared notes, or we may need to fall back to activating your camera and asking questions until the chat issue is resolved. Some folks are on, but a lot of people have not been able to log into the chat, and we apologize for the inconvenience. They're working on resizing the Linode server.
All right. Let me go through the rest of the B4 features, and then I'll have an option for people to ask questions. I want to get to delay stuff. That is actually what the latest coolness is. So before I test, I don't want to go too deep into this because I've been working on a separate presentation that will be part of the Linux Security Summit that's happening a week and a half from now. And this adds cryptographic attestation to patches by basically hijacking the DKIM standard and using it for our own needs. So this will add signatures to the email headers. So if you're just using any tooling that is not aware of the signatures, it will completely ignore them. It will just look like a regular message. But if you're using B4, for example, you will be able to see messages that have been cryptographically signed, and it will show it to you in a, This is how it will look like when you run B4 AM with a patch that actually has cryptographic attestation. It will say that it will check both the DKIM, and then if it finds a PGP signature header, it will say this is also signed by OpenPGP Casecook at chromium.org. If there is anything wrong with the message, it's been in any way, shape, or form modified, like the subject modified, or the from is modified, or the body is modified, you'll give you the bad zig, and then you will know that something is wrong here, so you can go and review the message and see what's actually is not correct about it. If you're interested in this more, please check out the Linux Security Summit presentation that's a week and a half from now, or just go to Patat is the library that is called. Patat is right there, and check out what it does. Start using it, dang it. So I'm not a kernel developer. I don't actually participate in the kernel development process. I'm a very close bystander. I see a lot of it. So I'm aware of a lot of stuff that's going on, but sometimes I assume things and I'm wrong. There's something I think it should be working this way, but you think it should be working totally different because the way I made it work is actually fairly inconvenient. So I welcome this feedback, and please submit it to me. Don't just, if you find a quirk in before that you don't actually think is useful, tell me. I will try to modify it so it actually does what is useful for most kernel developers. You can email tools@linuxkernel.org. That's probably the best place to do it. That's it. That's all about before. Any questions? Chat's not working right now, so I'm going to check the shared notes. Okay, nothing in shared notes. I'm going to plow on. And at the end, depending on how much time we have left, I will ask all of the questions, or answer at least all of them. So death by 10,000 mailing lists. Some other problem that we've come across is that and it's actually a common misconception, that there is no such thing as a Linux kernel mailing list, right? There is Linux kernel at V'ger, which is usually referred to as LKML, but a lot of stuff is CC'd to it and a lot of stuff is sent to it, but nobody's actually reading it. It's kind of like yelling into a fire hose. Maybe like a couple of people who are very dedicated, maybe like looking at what happens on the Linux kernel mailing list. But most of the time, it's just stuff is there as write only. A few people read that. So there's a V'ger kernel.org, there's infradev, there's linux.dev now. Where do I send this patch, right? How do I know that the patches that I send will be actually seen by the maintainer that this is aimed at? Getmaintainer.pl in the Linux tree will help you, but it is kind of daunting for one-off contributors, right? You have to know that you need to run it. You need to know that it need to run it as part of git send email. It can be complicated for folks, right? So can we harness the power of lore kernel.org for good, or for more good, for gooder? The new tool that is actively under active development is the public inbox local email interface. It's LEA. And if there's a joke here, is Lorelei, of course, is a common name. So LEA is a tool that can query remote sources and deliver them locally into your mailbox, or it can deliver them to your IMAP folder. I'll demonstrate in a moment. It supports search-based queries. It can deliver to local mail dears, to remote IMAP targets, and it can query lorekernel.org/all. What does it mean? Let's take a look at the maintainers file, right? This is just a random subsystem that I grabbed because it looked convenient, right? Let's look at the bits that are F and K lines. If you don't know what maintainers file is, the F file says, this subsystem is responsible for the following files: documentation device tree, RSD, drivers, OF overlay, drivers OF resolver, and K is the regex of any of the context queries, right? If there's a function that's called OF overlay notifier blank whatever, it belongs to this subsystem. They want to know about it. So let's take a look at how we can use this to formulate a lore kernel.org query. So these F lines and K lines translate directly to the following query, like the DFN, 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 or DF context, OF overlay notifier, right? If anything that mentions OF overlay notifier, I want able to find it. And if you download the PDF presentation of this and you click on this, you will find the results of this query. So LEA allows you to run this query and deliver the results into your local inbox or into your IMAP folder, right? There's a LEAQ-O is an important part here. Deliver it to my local mail deal folder, right? Query the remote lorekernel.org/all, and the -t, it says grab the entire threads, right? It's not just the matching messages, but the entire thread. If, for example, if you want to see the context of the conversation, if somebody mentioned your function name or your subsystem in a message somewhere deep in the thread conversation, you want to for example, grab the entire thread so it can review exactly what happened to lead to that mention. You may not want that. It can bring totally random, completely irrelevant threads, or you may want to just grab the actual message. And if you're interested, you can hit remember the 4 key that I mentioned. Just backfill that from localkernel.org. Now RT means received date, right? It says show me all the results that have been received 6 months ago until now. The ... nothing means it's an open-ended query. So starting from 6 months ago until now, because you probably don't want to receive the results for that have been sent, in the past 5 years. You probably want to change that to just 1 week ago. And you can also deliver it not just to local mail dir, but also to a remote IMAP folder. This is pretty cool. I've been using it. If you've received sort of a creepy notification or response from me when you mentioned before in your conversation, this is how I know about this. I'm not reading the entire mailing list, but if somebody mentions before somewhere in a conversation and I think this is something I should respond to, I will go ahead and reply. And this is how I've been tracking all of the mentions of before and the entirety of lowerkernel.org tracked mailing lists. So lay command has, once you run this query, right, you can edit the search that you've created. You can tweak search parameters. They're not set in stone after that. You can change the RT to make it wider or narrower. Usually after the first run, if you grab the 6 months of the results, after that, you can just say, just show me the last week of results, because I already have everything that's older than that. You can exclude things that you find that are not relevant and not this bracketed query. After you've modified the search, or if you want to get the latest results, you can do layup and then change the and then pass the folder that where you're saving this. IMAP folder also works. You can delete messages from the folder after you receive there, so it's not like you have to leave them there. You can delete them as usual. You've reviewed them all. You can just delete them all. They will not get re-added because Lay keeps track of the messages it has elsewhere. If you create multiple saved searches, you can just update them all at the same time with --all. There's any credentials that you have to use with IMAP server. You can save them you can set up the Git credential helper and store them locally. This way you don't have to continuously enter them. You can list the searches that you have saved. You can forget specific folders. This will just forget the search but not delete the results. So if you have a one-off query that you find everything that mentioned is back 6 months, after that you're not interested in it, you can just forget the search and keep the results. All right, this is really cool stuff. The status of it is under heavy development. So the examples that are provided work now. They may be requiring a few modifications a couple of weeks from now. The documentation is extremely sparse, so as usual for a tool that is being actively developed, we hope to provide ample documentation once the features stabilize. New features are forged all the time. Literally, if you monitor the public inbox mailing list, you will notice that there's a lot of work being done on Lay right now. You can install it locally if you want to play with it. I'd completely recommend that. You can read the install file. If you're running Podman and Toolbox and Fedora, I have toolbox instructions on how to do that. You just click that link, download the PDF, click that link, or go to publicinbox.org/meta and look for toolbox instructions. If you're in Fedora, that's very easy to accomplish. And this gives us some ability to do some cool ideas, right? We can do pseudo mailing lists, right? We can manage on our end sort of a query-based search, right? We can offer them as a read-only IMAP or POP3 in the near future. And POP3 is important because, for example, in Gmail, you can say source results, source this remote POP3 folder and add them to my inbox. This is kind of cool things you can do with Gmail. And it can let you do things like, instead of creating your own mailing list for your own subsystem, you can just say, you can list just send patches to the next kernel at vjur.kernel.org. My saved search or pseudo mailing list will find anything that mentions the things that are important to me, right? Just mention my subsystem in the email. I'll see that because my saved search will add it to my pseudo mailing list, and I'll receive the results. Or just send patches to LKML. I'll find them. It doesn't matter. Or to any mailing list. It doesn't matter. I'll see them, right? What this allows us to do, this makes it easy to onboard new maintainers. So if somebody comes on board and wants to replace your duties on a subsystem, instead of subscribing to like 5, 10 different mailing lists, you can just say, just receive the following the pseudo mailing lists, or you can run the following query, add the following POP3 to your Gmail, just source this IMAP folder to wherever you want to do it. It's one of the options. We can also potentially provide not just read-only, but read-write IMAP for individual maintainers. If you're a new maintainer coming on board, we can source this pre-saved search query and deliver it to a IMAP folder that you can just subscribe to. And then you can delete things from it. You don't really need to subscribe to any other mailing lists. Anything that's relevant to this subsystem will be delivered to this IMAP folder. So what are the main goals of the stuff that we're doing? It's cool things, right? What are the goals, right? We're trying to help maintainers scale. We're trying to turn up the signal, turn down the noise. A lot of patches arriving into your inbox is cool until you realize it's way too many patches. A lot of them are irrelevant. You can pre-filter them out before they actually even show up to your inbox. It helps us keep things decentralized. Anybody can set up a full mirror of lore-kernel.org. The mailing lists still, yes, have to arrive to specific inboxes, but this also makes it easy to move a mailing list to some other place. Now, if you move it, you can just say, by the way, it lives now there, and we'll just modify and source them from a different place. Hopefully, this is not confusing or frustrating. You can do it yourself with the lay command, but we also understand that it could be complicated to do it. So we're trying to see what things we can do on the kernel.org side that will make it easy for you by doing a lot of the hard work on our end, like the pseudo mailing lists or the IMAP folders that we pre-filter results into. We're trying not to break maintainer flow. The goal is not to break maintainer flow. If you don't want to participate in any of this, we're not breaking anything. Subscribe to mailing list, receive the mail. Anything that's working with you already, we're not breaking any of that. We're adding new tools and new features that you can use without disrupting any of the old stuff, right? There's no flag day that everybody from now on has to use this new system, as we know this works really poorly for everybody. And we also want to simplify things for contributors, new contributors coming on board. We want to be able to say, doesn't matter, just send the patch here. People will see it. Or if you want to ask a question, just send it to this and mention the subsystem you're interested in. The person who is responsible for the subsystem will see it. That's it. How to keep in touch. There's 3 mailing lists you should know. I know we're back to mailing lists, but we're still using mailing lists, so this is cool. If you want to discuss maintainer workflows, what's working, what is not working for you, email workflows@vjr.kernel.org. If you want to talk about the tooling before any of the other tools that I provide on the kernel.org side, there's a tools@linuxkernel.org mailing list. It's different from vjr, historical reasons. Let's not talk about that, right? Or just mention before in an email somewhere. I'll see it. This is totally normal and non-creepy. I guarantee that. If you want to participate in development of lay, give feedback about your lay usage, there's a meta at publicinbox.org. It's developed by somebody else working with Linux Foundation. All right, we are at 10:49, 10 minutes, 5 minutes for questions. If you have a question to ask, please go ahead and ask it.
And there are 2 questions at the bottom of the shared notes, Konstantin.
Okay. Yep.
You want to take a quick look at that?
What does the future, far, far future look like? Well, my goal is to add tooling that does not centralize things. And this is the hard part, right? We don't want to create an infrastructure that is completely central, where it also makes extremely easy to knock out, or just have one place where an attacker has to concentrate their attention to completely knock out the kernel development. if you have a Garrett server for kernel or a GitHub repository for kernel, or our own GitLab repository, self-hosted, often mentioned that why don't you just have a self-hosted GitLab repository for kernel.org? Problem is that we either have to have the beefy power of GitHub or Microsoft or Google to be able to withstand denial of service attacks on that, or we shouldn't even bother, because if we're creating infrastructure that can stop Linux development in its tracks for, if there's a 0 day, and then we have a denial of service that nobody can talk to each other to fix the 0 day, then obviously this becomes an extremely tasty target. So we need to find a solution that allows to keep Linux development decentralized and fault tolerant without making things any more complicated than it is right now. There is a project called, I'm blanking out on that, Radical, that uses that has a decentralized Git infrastructure with unfortunately too many crypto chain bits that I try to ignore. I understand why they're important, understand why they're focusing on some of the crypto parts, but what I really want to see is them focus on social parts of coding, like receiving patches, reviewing patches, keeping track of bug reports. And this is all supposedly coming. So what I hope in a couple of years from now, we'll be able to say, as an alternative for your subsystem, is instead of just using emails, if you want to use Radical or some other infrastructure like that, you can, without making it central. What about integration with Patchwork? Patchwork and B4 using different, are used for different things. Like B4 is read-only, right? So you don't need to, if you're not tracking state of patches, if you're not delegating patches, anything like that, you don't need to use Patchwork. If you are interested in features like this, right? If you want to be able to say, well, I've dealt with these patches, I've dealt with these pull requests, and I want to delegate the following things to a different reviewer, Patchwork is a great tool that can work with you. Patat library source is not in the same Git repo as before. It will, if it is a submodule that it can download and install. If you're installing before from a Git repo, you can run Git submodule in it, and it will pull it in. DMARC does work on LKML. Unfortunately, so DMARC requires DKIM signatures to properly work. If there's no DKIM signature, but there is something, there's a stupid setup, so there's a DKIM signature, but there is a DMARC policy, but no DKIM signature, and that doesn't work at all with mailing lists. So if you're sending patches to LKML, to V'ger, or to a number of other lists, then you want to set up DKIM. Unfortunately, if it's going through a Mailman 2 list, infradead, for example, then it breaks DKIM, and if somebody fixes that, that'll be fantastic. We also provide Linux.dev mail hosting, so we try to be extremely DMARC compatible there. So if you want a new mailing list, that's an option too. All right, I think I'm coming up on time. Last question. Okay. I suggest that any further questions that you have, if it's specific to B4, send them to tools@linux. If it's a workflow, like more of a wider scope, how about we do this, or how about we do that you send it to workflows@V'ger, and we'll be able to take it up from there. Dmitry,
did you have one last question, Dmitry? Dmitry, right. Did you have one last question?
You're
muted.
Can you hear me?
Yes.
Hello. Thank you for the great presentation. So I wanted to ask one question regarding the doomsday scenario you mentioned. Like if, say, there is a super critical bug that brings the internet down. So I wonder what's your thoughts regarding if we should optimize the developer workflow for this case, because it looks like it's super rare and I would assume it can be handled using, say, email or some older mechanism, but like the thousands of the patches we have, I don't like it. It looks that they're penalized by this potential scenario. Yeah, thank you.
So currently we are resilient to the doomsday scenario, right? So if there's a 0-day and kernel.org is DDoSed out of existence, then the individual developers can work with Linus directly. They can send email. If Gmail is also targeted, then Linus can communicate via some other back channel saying, I have this email address nobody knows about, send me patches there. There are ways to attack that too, but currently it is too complicated to address that, right? So how do we make sure that we also have address the doomsday scenario and make it easy for automation? I understand that automation is a different subject here. It is hard to work with patches sent to mailing lists, even with all the tooling in place, and to be able to provide useful feedback about the features, about the patches, like saying, especially when you don't know where in the tree the patch lives, right? I didn't want to go too deep into that because we would just be going down the very deep rabbit hole with how do we automate it better. But I'm trying to provide tools that maintainers can use right now, and I wanted to leave out the how do we switch to a different workflow that allows for better integration with automated tools as a topic for a separate discussion.
I see. Thank you.
Mm-hmm. Okay, Ted, I'm ceding my place to the next presenter since they're supposed to come up in 5 minutes.
Yes, thanks, Konstantin, for your presentation. I'm going to be dropping a drive link into the shared notes, and then I'm going to be copying all of the questions that were put in the shared notes into that drive link. I think there were 1 or 2 questions that we didn't have time to answer. So like I said, I'm going to create a drive link, copy all the questions there. And then if you could maybe take a look at that and answer them in the shared Google Drive doc, maybe that'll be a short-term workaround. And then I'm going to be clearing the shared notes for the next presentation. So that was going to be my plan. And thanks so much for giving your presentation. All right. Okay, so we're getting set up for the next presentation. I'm going to switch the slides to that next presentation. And who wants to, should I be handing off the presenter status to Alex or Jesse?
Yeah.
Alex. Okay, great. Let me set up the presentation. Okay, and now let me find Alex. Oh, there you are. Okay. All right, Alex, you should be the presenter, and why don't we wait just a couple of minutes, 2 minutes or so for the top of the hour, and then we can get started.
Ted, I'm having issues with the matrix chat. if there's a question addressed to us, to either one of us, I think Jesse is also having some trouble.
Yes, there are still issues with the matrix chat. The planning committee is frantically working on that. What I suggest people do is switch to the shared notes and add the questions to the shared notes so that you guys can, the presenters can see the questions, and then we can use the shared notes as a workaround until the matrix server can be brought back online. Apparently, it's a single-threaded Python script that worked fine for the town hall, but is falling over in the load of the full conference. So they're currently working on it. So we're going to be using the shared notes as the temporary workaround. All right, and with that, we're at the top of the hour, so let's get started. Next up, Alex and Jesse are going to be talking about scaling the Chrome OS development, and I'll let them take it away and introduce themselves.
Hello, so a quick intro. I'm Alex. I'm a kernel platform lead, or generally a platform lead in Chrome OS. Jesse, you want to quickly introduce yourself?
Yeah, my name is Jesse. I lead the team that oversees the base operating system development on Chrome OS. So that includes kernel, firmware, hardware security, a bunch of other stuff. So, hi.
Yeah, and as I added to the notes, two things we really love getting in our emails is questions and CVs, so feel free to send any one of them. All right, let's talk a bit about what the agenda today. So we want to cover a bit about our kernel lingo, so what's a rebase, uprev, and then what is continuous rebase in our terms. We'll touch base about how we try to test and cover the RC kernel in our testing ecosystem. And then we'll talk a bit about some of the pains we have with upstream and with implementing our upstream ideology, per se, in Chrome OS and with our partners. Please feel free to stop us at any time to ask questions. This is very much a discussion-driven or question-driven presentation.
Yeah, just raise a hand or throw it in the notes.
All right, so generally speaking, the Linux kernel in Chrome OS comes in many versions, from 3.18 all the way to 5.4, and we will be starting to embrace 5.15. We'll talk a bit about what it entails. And each of these kernel versions ships with multiple platforms, and each platform has multiple devices. So many millions of users per each kernel version. And the kernel versions, or the specific kernel version a platform ships with, is selected when a platform is brought up. We typically try to select the newest one because it's easier to do a bring up. There are exceptions to that. In some cases, we would do a refresh for a platform, and then we will choose the kernel version that the original platform started with. What is a rebase? So the way we call a rebase when we move or when we adopt a new kernel into our repos, and then we will Chrome OSify it. What does that mean? That we'll basically rebase all the non-upstream patches, and we carry some of these, on top of the newest kernel, and we will create a new repository that new platforms can choose to use from that point on. It's a process that takes, or at least used to take, several weeks. It's led by several of our TLs and different teams, different technology teams. And basically the rebase is broken into topic branches, and each team as an example, the storage team will take a look at storage-related topics, will debug them when it's not working, and will work on conflicts of Rebase. And then we have an uprev. An uprev means in that directory structure moving a platform from one kernel to another. So from time to time, we uprev platforms. We want to keep them as close as we can to upstream. And we also want to remove the amount of kernels that we maintain and ship platforms with. And so we're basically, sorry, Jesse, take it up from here.
Yeah, so this is taking that Rebase kernel that Alex mentioned and actually deploying it out into the fleet. And there, as you can imagine, this is a little bit of a process. We don't dump the new kernel on everyone all at once and then try and fix up the regressions afterward. We try and do a lot of internal testing. We do what we call internal dog fooding, where we have internal users use it and report issues. And we try and fix all of that up before it gets out to beta channel. There's a feedback mechanism built into Chrome OS that we use heavily for this process, plus all of our internal testing. So the Android CTS test suite actually covers quite a bit of our quality, in addition to the Chrome OS testing that we have, our automated testing system. So there's a lot of testing that goes into it, but then we actually today rely quite a bit on feedback reports from internal users and early users, more than I would like, just because our test coverage is not perfect. And we'll touch on that later. But we're trying to improve that by getting some of our tests up into kernel CI so that we deal with fewer upstream regressions. Although when I first started, I thought that dealing with upstream regressions might be more of an issue than it's turned out to be. We do have to deal with upstream stuff, but that is more around dealing with stuff that isn't upstream. So surprise, surprise. And historically, Chrome OS had been pretty good about this. Lately, there's been some drift in the past few years with some vendors not being able to push things upstream for various reasons. And then we have to deal with that at uprev time. So that can cause delays. But overall, I really want to get to more automated test coverage here. I think the free desktop graphics model is actually a pretty good one here. Our graphics team just ships upstream because they've got good enough API test coverage and compatibility test coverage with their API traces. So I'd like to get a similar level of confidence from our kernel side of things. And that most of the time here is not really spent on working on bugs. It's actually spent on administrative stuff, figuring out if a bug that's been reported is related to the new kernel and is actually a regression. So most of the work is kind of meta work, but we're also working on that. So Alex is going to comment on this part, but they can be tough to predict how they go.
Yeah, so when we first started, or historically, we tried to uprev a few years ago, and then we decided to pause that activity. And then 3 years ago, we resumed upreving, and now we're going at it every other year for a platform. And what we discovered is when you uprev an old-ish platform from 4.19 to 5.4, apparently there's a lot of breakage. Stuff doesn't work, or typically every big component doesn't work. Something is broken. Many or most of it is typically not related to upstream, but some is. And when we dug into upstream, apparently these platforms are not tested, or obviously not all platforms are tested. And so we're trying to increase our test coverage with upstream. And that is for us to be able to plan and resource an uprev, because unless you do that, you really don't know how deep the rabbit hole is. You only discover that once you try to uprev. And then it becomes a test-driven activity where you run a bunch of tests. We have thousands, and including CTS, millions of tests that we need to pass. And they fail, and we try to fix them. And And this is an ongoing activity of trying to fix all the tests that are failing to match the existing or the shipping kernel. And then, as Jesse said, we release that to dog fooders, internal users, and we use our dev and beta channels to allow some feedback from the community. But that's hard to step because we don't know how many engineers it will take to do an update. So we kind of thought of, sorry, yeah, go ahead.
Oh, I was just going to expand on what you mentioned about the testing. I did say that like a lot of the time is spent looking at feedback reports and figuring out if things are regressions. A lot of the time lately has also been spent on fixing tests that are actually not broken, but appear to be broken when we go test against a new kernel because of some timing issue or some kind of small compatibility problem with the test itself and not with the feature that it's supposed to be testing. So I think that's, you know, unfortunately fairly common with functional testing, but it's something that we're also working to improve.
Right. Thanks for that. And so maybe a way, the thing about 2x on the capacity, that's the way we try to test. So we have A/B testing for the kernels. We have our own CI system that is running, and we load kernel A on half of the devices, or almost half, and then we load kernel B and we compare results. So nothing fancy about that, but it's an ongoing thing. So we constantly test. We always deploy a new build, and we test that as we go.
I was going to mention one more thing. I forgot to mention it on the earlier slides, that Alex showed that list of the kernels we support, which looks like a nightmare and is less of a nightmare than it used to be, but it's still a challenge. So our goal is to reduce that to 2 kernels in the field, host kernels anyway, and then 1 kernel that we're working on to push out to replace the old one. So that's the goal. Like Alex said, new kernel every other year on every device. That's getting a little more complicated now because we've got more VMs in the picture, and so each of them has their own kernel that we've got to deal with. But in some cases, that gets dealt with for us. Like, for example, in our Android VM, one of the motivations for moving to a VM was that we can leverage the GKI kernel from the Android side, which Greg maintains a big part of that and makes it really simple. Just move up and don't have to worry about compatibility testing and everything like that, because we have confidence that it's going to work.
All right, so introducing continuous rebase. So we thought about how we can improve the testing of release candidates and upstream and actually catch breakage to our devices as they happen and work with upstream and work with our internal teams on making the upstream kernel healthier. And so basically what we're doing is we're basing our patches on top of every RC. So the first time we do it, it's kind of hard. There's a lot of conflicts. But then we incrementally add the conflict resolution on top of the new RC, and so it becomes incrementally easier. A huge kudos to SemiHalf, our contractor that are actually doing that, and they have came up with amazing innovative tools to do that. So we basically rebase every RC, and we have added a new repo that was also in the slide with the directories. The first one, upstream. So upstream is a repo that basically changes on a weekly or a bi-weekly basis with every RC release, and the added latency of us rebasing on top of it. And then we have, for each new platform and for each platform that we uprev, we run a continuous test against upstream to see that the testing status is the same as the shipping kernel. So from the very early days of a platform, when we bring it up, we actually track the health compared to upstream. We have a few examples. I've added a few links. We have more of breakage that we caught, reported, and fixed on the upstream kernel. And using this way, we have tests, example, internal tests that are failing for the different teams. We can get engagement from our developers. So we send emails. We have an automatic tool that just creates bugs for every failure, etc., etc. So now we have a lot more involvement internally for upstream Linux, and we don't have to wait until we have a base on top of it. All right, report the failures. So we have spent quite a lot of time thinking about how we report the failures internally. It was the domain of the problem is a bit more familiar or easier to us. And so internally, we feel like we have evolved enough so that breakage is both caught and addressed in a timely fashion. Our upstream work should be better, I have to admit, and we are working on that. So we're looking for ways to report breakage and share our testing results with upstream. We are planning to start in the immediate time frame to look at the integration with kernel CI and try to inject errors through that path. But we are also open to other suggestions. So we had different thoughts on the matter, sending emails, using Bugzilla or whatnot. But again, it needs some amount of work on it. I see there's a question being typed. Jesse, do you want to take that?
Yeah, so depending on how you count, that is actually our goal to get down to 2 kernels out in the field. We actually share the kernel version, and we deploy the same kernel version on our ARM devices as we do on our x86 devices. So the uprev targets the whole fleet eventually. The process of rolling it out is kind of staggered. So it might hit an AMD device and then a MediaTek and then Intel or something like that. But it'll be the same version, and eventually it'll roll out to everything, and then we'll get ready to roll out the next version onto those devices. But I'm not sure if that's what you're asking, Arn. I don't know if you want to unmute or comment, but. Oh, the same image. No, Alex, comment on that's actual kernel config images.
Right, it's not just the config, but our image includes, so we don't separate the image of the kernel out of everything else. We have one image per platform. So you will still get an image per platform.
And we build, yeah, the platforms tend to have configs with their particular driver set, right? So
Schwan is
no initRD or anything. And yes, oh, Linux Next. We have been talking about that. I don't know, Alex, if you want to comment on.
Yeah,
on
it's high. It's high on our priority list. We see the value there. There are actually other trees besides Next. DRM tip is another one that we see a lot of value testing as we go. But before we do, we want to hash out our reporting strategy, especially upstream, because if that's the most important thing. That's how we scale and get everyone's involvement, and not just a handful of people. So once we do that, we will start integrating more and more trees and Rebase on top of these. I hope that answers.
And I actually hope to expand this. One of the things I would really like to see is the ability to just run, like if you have a Chromebook, select a channel that gives you, or select a flag that gives you the upstream kernel as your kernel for that device, and then we can collect feedback reports and telemetry and everything, and see how well it's working. We've got a little ways to go to get there. Some upstream backlog and then functional testing to make sure things like audio don't break when you switch over. But that is something we're working towards for sure.
Right. So another question, are these tools for testing RC candidates available? Yes, everything we're mentioning here is upstream and public. So I can follow up. There is quite a lot to talk about the actual tools for rebasing. These are upstream. The RCs, the rebased RCs are also upstream. So if you go to the upstream folder that I pointed into from slide 3, that would contain the latest RC, but all of them can be accessed if you look at our manifest. That's how our repo structure works. It points to a namespace, merge / continuous / something, and then git ls remote would give you all the different branches. The actual testing environment or our continuous integration environment, no, that's not open and not available for the public from obvious reasons. Do you use UML at all for testing? No.
We do a lot of virtualization testing though. So we'll build VM images for like GCP and do a lot of testing there, but not UML specifically.
All right, let's see.
So yeah, this touches on what we've been talking about. So one of our kind of guiding philosophies in Chrome OS is to upstream first, and that applies to all of our projects. It's complicated, as you might imagine. We've got a lot of partners that we work with, a lot of different projects that we're engaged in. On the kernel in particular, we track everything with metadata in our commits and our Git tree. So if you go to the chromium.org Git tree and check out the kernel, you'll see a lot of patches tagged with these things. And there are a few variants of these, but we've got like upstream patches, which means we've just backported an upstream patch wholesale, and we pull it in, and that happens quite frequently because we need some new feature or a bug fix or whatever. And their variants there might be from Git, where like it's queued in Git, to head to Linux for the next release. We'll tag it that way so that we know, to check it for our next rebase, that we might be able to drop it out. And backport just implies that we've had to do a little massaging. So it's the same thing. We pull it from upstream, but we've had to adjust it a bit. So that way it kind of flags to us, hey, if we've got a problem in this area, we can look and make sure the conflict resolution was done well, or maybe we broke something in that process. From list is something that's a little bit more on edge. We don't like to see this as much because it means, okay, yes, the patch has been posted, but not necessarily accepted yet. It's better than nothing because it means at least the process has begun. But in some cases, we see people using this to kind of tag it with something more positive than Chromium, and then they never follow up on it, and it never gets accepted upstream, and then we have to forward port it in continuous rebase or next full rebase. But like I said, it's better than nothing. But we do want to minimize these. And then Chromium, these are the patches that, like, for whatever reason, we can't upstream, or maybe have been rejected from upstream, or require some significant re-architecture, or in some cases are experiments. So we do actually push stuff out to our fleet to get data on, hey, is this approach even worthwhile? So the core scheduling stuff that Joel worked on and continues to work on is an example of that. We had some Chromium versions, tried a few different things, and then Joel would settle on something and push the final result upstream. Or the stuff that Yujiao's been working on with MGLRU, the new memory management framework, where we collected a bunch of data, got some really awesome results, and decided, oh, this is pretty significant, so we move forward. And then, of course, there's the kind of perennial headaches of proprietary graphics stacks, where we might keep an open source or a closed source kernel driver for the graphics stack, and there's no point in pushing that. There's no open source user space, so we have to carry those, and those cause some pain. I think the vendors have gotten a little bit better at making those pieces portable and minimizing the API service and all that, but we would still vastly prefer a fully open source stack like we've done on the Qualcomm devices lately. So on the next one,
let's think maybe there are two new questions. So are your tests open? Can you share them? And or add them to existing kernel test suites. Yes, they are open. I can follow up. I haven't included links on the slides. That's my fault. If you want, please send me an email. We can follow up. They are open. You can just Google test and Chrome OS testing and whatnot. You can run them on any device that you have. They are not specific to kernel, right? What we test is the entire complex setup or system that we have. We care that Android runs and that touchpad and touch screen works, etc., etc. So our testing is basically to test the different domains and capabilities, software or hardware, from our perspective. And when we change the kernel, we compare them A/B for a different kernel. So the failures will not, or the failures will map to kernel changes, but they will not be specifically testing kernel components or kernel suites. I hope.
Yeah, it's not like LTP or something where we're just hitting a system call with particular arguments or something like that. They tend to have some higher level components. Some of the tests even include Chrome automation, which is really important for us. And I personally think it's really important for overall kernel testing to see how higher level workloads like Chrome behave, especially in light of like scheduling changes or memory management, where some small change a kernel developer might think, hey, this looks great, it works great on this server workload, but maybe it really poorly interacts with interactive performance or causes responsiveness to really decrease for an interactive workload. So like I mentioned earlier, a lot of this stuff we're trying to push into kernel CI. So we've got some work with the kernel CI team to have Chrome OS as one of the OS images that we can deploy, and then we can run these higher level tests without too much modification. There's been some work to take some of our testing and port it to like a Debian type environment as well, so that it would mesh better with the existing kernel CI infrastructure. So we definitely invest heavily and spend a lot of time on that. We've done a couple of hack fests with them. So that's something we'll continue for sure.
The next question. Sorry.
Yeah. On the next question, the long-term efforts. So this is a big part of my job, putting pressure on our partners.
There's a slide about that though. Let's keep it to that slide. I promised Lauren in the email exchange before this that I'll include the slide, so we have one. Jesse, numbers on Chromium upstream from list. I think you have some numbers.
We do. Gunter creates a monthly report for us that we share at our kernel kind of all hands meeting. We do tech talks and stuff, and so that's where we kind of beat the drum, like, please upstream, don't let these numbers get worse. So yeah, we do have numbers on that. I don't remember off the top of my head, but it's on the order of hundreds, I believe, that we're still missing from the upstream. And the from list and upstream numbers are, like, the upstream numbers are really large. From list is pretty big. Chromium and from list are the ones that I worry about the most. I could pull that up in a minute if you want to take on the next question.
Right. Are there plans to provide images that prefer the open source driver, like Mali and Adreno GPU drivers, in a development/upstream channel? Jesse, you want to take that one as well?
So we have that for Adreno. The latest stuff we're shipping on Qualcomm devices is all Freedreno based. So Rob and Christian's team have been doing a lot of work there. So that's super cool. We do have a variant of for some of our other platforms. I think it's just the MediaTek ones, because the other ones are IMG based. If you pull down the Chromium tree, you can pass a use flag when you do the build to get the Panfrost driver stack. It's not very well tested for us right now, because we haven't, like Alex mentioned, we have some testing infrastructure limitations, and we're kind of capacity constrained. So we don't have an automated testing set up for that yet. I'm hoping we can move more in that direction eventually, but again, that gets back to our partner relationships and everything else. So, but it is something that you can run if you want to. jumping back to the other question about the Chromium patches, our top offender is our media subsystem in the kernel, and we've got 54 as of last month Chromium patches in that area. So that's like drivers, media, V4L stuff, things like that. So that team has been, it's actually come down a lot. We used to have almost 200 there. So that team's been working to kind of address that backlog, which is great. But the next one down is some of the VirtIO stuff we've been working on. We've got 30 some patches there that are tagged as Chromium. And Cross EC is another one, our embedded controller drivers. We tend to see some churn there as we bring up new platforms and add a few new EC features or interfaces on a per platform basis. But a lot of that is going to be dropped now because we've moved to a new way of handling our sensor data. So anyway, that's kind of order of magnitude for some of our different subsystems on the Chromium patches. So on the upstream side, so I think hopefully we've made it clear that we want to upstream everything. A lot of our people work really well with upstream and sometimes even enjoy the work. So it's something we want to do. We want to make Linux better. We want to make our own lives easier. We run into kind of, I don't think there's any surprise here. The people that I see on the attendee list here are all familiar with all of these issues. One of the big ones that we deal with is maintainer responsiveness, and this affects probably our vendor partners more than it does us in terms of getting stuff upstream. So sometimes you have maintainers who are like, really on the ball. They tend to spend a lot of time on assigning reviews to other people in a subsystem area or getting reviews themselves and providing really actionable feedback to document a path, map out a path to getting a particular feature upstream. Other maintainers, for whatever reason, don't spend a whole lot of time on it or provide, very vague feedback at best. I don't see Russell here. I put architecture maintainers here as a troll for him, so it's falling on deaf ears because he's not around. But anyway, that has been a problem in the past. I think it's much better now, like on the ARM side, especially. We're mainly focused on the 64-bit side of things now too. So there's a whole bunch of sub-maintainers there that we're happy to work with. And then some things are really, really stuck. And one example here is memory management. So there have been some interesting discussions lately with like Yu Zhao's patch set on MGLRU or Willie's stuff with Folio, where it doesn't seem like we have a clear path forward or even agreement among the major players about how we would move forward in this subsystem. I mean, some of the threads I've seen indicate like we just shouldn't change anything because we might break something. And while that's true, it also kind of leads us into an evolutionary dead end. So, I have a wish list here of what I would love to see here. I know we've got a good code of conduct. Generally, I think the culture of the mailing list and community has really improved over the last few years. But I think from a maintainer perspective, I think there's still kind of a lack of consistency. And so I thought it might be nice to have kind of some metrics around responsiveness, around acceptance criteria, around as a maintainer, what is expected of you in terms of giving people a roadmap, either a strong knack with some really clear reasons or a pathway out. And I know this is a challenge given the consensus nature of the community that we've developed here over the years, but it would be nice to have some more consistency here. The other usual stuff applies, right? Like the yak shaving and people saying, oh, well, why don't you just change your product architecture? If you ship this board instead of that board, you wouldn't have this issue, or things like that. It's like, coming in to a discussion with that kind of approach is not that productive, typically. So like getting back to the memory management side of things, one of the things I think would be great to see is some kind of consensus around what benchmarks are important. So one of the things Yu Zhao struggled with on MGLRU is just getting some engagement from some of the big contributors who deal with cloud infrastructure, for example. So we have some internal data, but that's not sufficient for justifying an upstream push. We'd like to get some other folks on board, but he's had a hard time getting agreement on that, or even what's important. I think generally speaking, in this particular case with MGLRU, like it seems to be almost universally a huge win. And we're going to be publishing some more data that we're just spending money to get in order to justify that. But I still see this as a problem, and it's bigger than just memory management, right? This is across the board. You know, how do we not just get agreement on a patch, but like get an agreement on what's important for that subsystem, so that other patches that come in later can kind of funnel in the right direction. Another thing that I wanted to bring up is experimentation. So I mentioned that we do experimentation and collect telemetry as we're doing development, and this is a really important part of our development process. It lets us get real-world data from a ton of data points and really inform our decision-making about whether something's going to work, or if it has some corner case that we didn't consider and it's really blowing people's machines up. And I wonder how we can enable this in the Linux community more broadly. You know, we have revision control, we can revert, but on the other hand, it's like one shared tree, right? So I just wonder about this. I don't have a particular idea about how this might work, but I think it would be pretty valuable to see something that would enable more experimentation in the upstream kernel.
There's a question. Have we considered maintaining a stock subsystem?
Oh yeah, we would be happy to maintain the whole memory management subsystem.
Right.
I'll throw people at it tomorrow if that's what it takes. But I think that's not the issue. It's more that we have both competing priorities among the different stakeholders in a given subsystem, and kind of competing development philosophies. And there's no tiebreaker. So in a sense, it's like the development process lacks a system of justice to arbitrate between parties in this case. And you know, the protest saying goes, no justice, no peace. And I think that's kind of where we're at in some subsystems. But it's just overall a challenging problem because you have multiple stakeholders. Their viewpoints are valid. You know, their competing priorities are valid, but how do you reconcile it? In the case of memory management, like in my view, you know, maybe it makes sense to have a different memory management subsystem for 4 GB systems versus 1 TB systems. But a valid pushback on that as well. Then you've got split testing, split effort, and you know, one of them is going to drift relative to the other, and one of them may be maintained better than the other, and that's true, right? But if you've got enough people on both sides, maybe that's fine. But again, that gets back to like, what are the criteria? What are the important benchmarks? I don't know.
Based on the amount of writing, you touched a nerve, Jesse. Is the main memory management maintainer employed by Google? I don't know, maybe.
Hugh, I mean, he was a key maintainer, right? Yes, and he's on the cloud side. And he's viewing it from the cloud perspective, but we've got people like Johannes too, right, at Facebook, looking at it from a slightly different perspective. And I think both of them tend to be very conservative, which, like I said, is valid. But how do we move forward? I don't know. And just because they're employed here doesn't mean we can like say, Hugh, you will do this, right? I mean, that's not that's not how we work here anyway. Oh, Andrew, yes. Well, Andrew, yes, but he tries to stay very aloof as well. So again, he's not going to receive direction from Google about like merging a patch. That's not how we manage this stuff.
Right. Red Hat Linux has similar problems. Some bug fixes are stuck on pushing upstream +1 to any solution. All right, partners. I promised to Loren now twice to talk about that. So we obviously interact a lot with partners. We build platforms. They consist of SOCs and different components, each with a vendor, and they all need to upstream. And from time to time, or quite a lot, we have to police our repo to make sure that no downstream patches are submitted. So the general approach with partners is that we don't allow Chromium patches. So Jesse said that media substance system, we have 54 Chromium patches. That's not a lot, right? So the general ballpark is probably a few hundreds of patches for the entire tree, and we're trying to reduce that as we go. So we treat our upstream debt with tremendous seriosity, or we are very serious about that. We see the pain later when we uprev platforms and we try to maintain the quality, having downstream or from list patches that haven't landed into any maintainer's Git or upstream. They translate into tremendous money, right, or time that we spend on them. And so generally with partners, we have to police our ideology of upstream first. And so partners have to ship patches upstream. They cannot land them in our tree without that, period. Yes, there are exceptions. We can discuss them, but all with very good reasons and multiple hours of meetings and documents, design docs of why we actually need them. But to that, we, as Jesse said, we have different tags that we can land in our tree. We have from list, from Git, and from upstream. So when a partner, or even ourselves, when we upstream a patch, we don't wait until it lands upstream for obvious reasons. The time it takes to land, or from the previous slide, one can understand it might take some time, and we still are in the business of shipping platforms to users. And so from time to time, we would land a from list patch in our repo. But then the person that lands it is on the hook on reverting it and replacing it with the upstream version of the same patch. We typically maintain or track this depth in our internal bug tool. We create a bug for each of these CLs, and we try to revert them on this kernel, or later when we're based to a newer kernel, we drop every from list and from Git patch that actually landed in upstream. We drop it and we take the upstream version. So Lauren, I hope I've answered your question. I see. Well, again, as I said, yeah, feel free to reach out. As I said, and I have to say again, we really like getting questions from upstream. So feel free.
Yeah, and on some of those, I mean, I know, Laurent, you're working on the new camera API. I think that the new API is a lot more, I mean, it's a better designed API for current needs, right? Or at least for our needs. I think there is some concern among folks that it would make it easier to do, closed space, user space stuff, kind of like happens on the graphics front. But I don't think that's a reason not to do a good API. So like I said, a big part of my job is pushing on vendors, leaning on vendors, putting pressure on to make sure things are open. And so I have done that on the camera side, and I'll continue to do that. One of the issues with ISPs and image processing in general is there's a lot of vendors in that space. It's not necessarily as standardized as the GPU side of things. So we could probably do better in terms of having common low-level programming interfaces. Something like WebGPU or OpenCL type stuff for ISPs. That might help with unification, but right now I think it's still kind of Wild West out there. But anyway, it's definitely easier for us if the full stack is open on Chrome OS. So we continue to tell vendors, please give us a full stack.
So we basically have 1 minute, and I think we've answered all the questions in the show notes.
One last, I guess, call to action. I mentioned Kernel CI a couple times. We've been seeding the Kernel CI lab with like lots of Chromebooks. So please, submit your tests there for your subsystems. Get coverage that way, and respond to bugs, and knowing that you'll get some coverage on like desktop class systems. A lot of Chromebooks there, ARM and x86 both. And like Alex said, we're always looking for good people. So
Yeah, don't hesitate on that. All right, thank you everyone who spent their morning or evening with us.
Okay, thanks, Alex and Jesse. Just as a reminder, chat is still seems to be a bit unhappy at the moment, so we're using shared notes for questions. I will be very shortly clearing the shared notes and transferring all of the questions to the Google Doc link, which is at the top of the shared notes. If there are any questions there that aren't answered, Alex and Jesse, if you could take a quick look and add any answers that you might want to that, that would be great. And I'm sure if we need to start further conversations, there are plenty of venues where we can have that. So thanks again, Alex and Jesse, and we have about a 15-minute break before we get started with our next talk. Hi, so we're at the top of the hour and it's time to start the next session. For those of you who may have just joined, you may have noticed that the chat server, the Matrix chat server, is not particularly happy right now. The Linux Plumbers Conference folks are frantically trying to work on that, and our apologies for the disruption. As a short-term workaround, we're going to be using the shared notes for questions. And there is a drive link where I have archived questions from the previous sessions today, and that's where those shared notes are. So if folks want to add questions to the shared notes, that'll be the easiest place to put things so that Mike can see them. Alternatively, as we've done in previous years, you can turn on your camera and wait to be acknowledged, and then you can ask the question via audio. So those are the two ways to ask questions. With that, why don't I turn things over to Mike, who's going to be talking about representations of physical memory. And I'm going to make him the presenter so he can get going. And thanks a lot, and over to you, Mike.
Thanks, Ted. So I'm Mike Rapoport. I work for IBM Research, and one of my areas of interest is boot time memory management. I maintain MemBlock, which is mostly boot time allocator and memory management before the main page allocator starts. And in the course of my work, I've seen a lot of things that probably could be done better with the respect of interaction between architectures and the low boot time memory management code. So to start with, there are a lot of diversity in the interaction between the memory management and the architecture, and how the architectures define and pass the information about their memory configuration to the generic virtual memory management layers. Now, this is actual command from x86 setup code that has like nearly 10 max PFN with prefix and suffixes, so that one of the developers took a second to know that explicitly. And this is not much different on other architectures, and this diversity and the lack of coherent representation of the physical memory across the kernel leads sometimes to some unexpected effects. There are subtle bugs that we need to trace here and there. There are difficulties in the memory hot plug, memory hot remove, and so on. For the most part, physical memory is represented by the memory map struct page, and it works really good for cases when the memory is flat, when there is no memory hot plug, and when there is no KExec that architecture supports. So these architectures that actually fall into this category, and probably these are not most exciting examples of what you of the machines you can run Linux on. Now, whenever we add some complexity, and whenever the things became more interesting, there are various effects that may be caused by things that by the things by lack of consistency between, for example, memory map and the actual physical memory layout. For instance, for systems that use sparse mem, a memory map can cover holes in the physical memory, and there will be indeed struct page for these holes, but there won't be a memory. And there is a long-lasting confusion, especially in the ARM code, that PFN valid actually means that there is memory, although it means only that there is a memory map. And next, there are systems, there are architectures that use that free parts of their memory map to save memory which is precious for them, and to reduce memory overhead caused by the memory map. And these cases also need to know how to properly, and I'll talk about them a bit later. KExec adds yet another level of complexity, and memory hot plug, hot unplug is probably the most complex case for the lack of coherent representation of the physical memory in the kernel. The systems that decide to free parts of their memory map need to define a custom PFN valid implementation, because the generic PFN valid implementation just takes the PFN, it subtracts the base PFN, and then you can access a struct page, and then you can dereference struct page, and then you can get null pointer, just because memory is not there, because it was freed in the init time. So there are a few of the architectures that do it. It's ARC, M68K, and ARM. And ARC may has up to 2 memory banks, so it simply uses 4 variables to check if a PFN belongs to the area actually covered by the physical memory. If it is, then we know for sure there is a memory map, and then PFN is valid. M68K has a neat trick. They have a virtually contiguous mapping of the physical memory regardless of the holes in the physical memory. So for them, PFN valid is alias to virtual address valid, which means it's present in their direct map. And the ARM relies on memblock, and the ARM is one of the architectures that keep memblock after the boot. Is so PFN valid when there is a memblock registered memory, and it worked really nice for older ARM systems with 1 or 2 memory banks. But when things become more complex with the addition of a CPI to ARM32, each PFN valid actually takes much longer time than it probably should. And I can say I have a good solution for this. Probably reconsider the trade-off between memory savings and the efficiency of PFN valid. Now, there is KExec that relies on resource tree to find memory where the bits of newly executed code and data will be put. And for that, it uses system RAM subtree in the IOMEM resource tree. I'm not sure it was a really good design choice, but well, I wasn't around back then. I don't know, maybe there were no better alternatives. But the problems it created is that systems other than x86 have really different representation of the physical memory in their firmware and in how they treat physical memory. So it may happen that system RAM can actually point to firmware blobs that are never exposed as system RAM in x86, and these firmware blobs can get overwritten by executing kexec. There is also a lot of duplicated code in Arch that registers memory, system RAM memory resources, and then reserves kernel resources, and then reserves different resources on every architecture, depending on what bugs they hit during their implementation of kexec. For instance, ARM64 has very special treatment for their no map regions, and RISC-V has, I think, the most complex functions that registers the system RAM resources, and this whole pile of code requires maintenance, and the resource tree and whatever firmware representation there is in the Arch code requires constant thinking with one another. So any change, for instance, addition of a CPI to RISC-V would require yet another pass-through update of IO memory sources, and who knows what bugs will hit there as we go. And the memory hot plug has its own way to represent the same physical memory. Originally, it was hidden behind, it was hanged, I'd say, from devices that visible to CSFS, and there were structures, there are structures called memory blocks. Each memory block represents a block of memories that can be removed or plugged on the fly. Each memory block has its corresponding device node, so that it will be accessible via sys devices system, and user can have some level of control for memory hot plug and hot remove via sysfs. At some point, the initialization of all the memory blocks at cold plug time became really expensive on these systems with terabytes of memory, and on top of the CSFS entries, there is what's called a local cache of memory blocks. Is an X array of all memory blocks in the system. Now, whenever there is an actual update for the physical memory, such as plug on plug, memory hot plug code needs to update multiple data structures. It has to create the memory block and the device node and CSFS entries for the new memory bank, or on the contrary, it has to remove them when the memory bank is removed. Then it should register IO memory source under the system RAM hierarchy, sub-hierarchy. And for architectures that keep memblock after boot, like ARM64 and the PowerPC, they also need to add a memblock entry, because their PFN valid or some other kexec code relies on memblock rather than other representations of the physical memory. So what we have at the moment, we have to kind of recap, we have several representations of the physical memory, like a subtree in IO memory resource. We have memblock for several architectures. We have memory blocks in drivers based memory for memory hot plug hot remove. And on top of that, we have a specific data representing a physical memory layout for instance, low PFN, max PFN on ARC. We have MXT6K memory array or PARISC-P memory ranges, which are very similar to Memblock, but for historical reasons, they remained untouched as is, so they are still there. And we have more complex beasts like x86, E820, x86 NUMA MEM-Info, and we have PowerPC, DRMEM, logical memory blocks, which kind of duplicates memblocks in a way. So all of these essentially duplicate each other in that way, or in one of the ways. Now, what we are trying to, what we have, and I'm going to try to explain my thoughts about having a more coherent model. So what we have is, let's start with what is physical memory. Physical memory in most systems is a collection of continuous memory banks. Now there is an exception of x86 first megabyte where things gone a bit different because of their history, and nobody would ever need more than 640 kilobytes of memory. But for the general case, there are DIMMs or soldered memory or whatever, and I doubt hardware designers would try to complicate these things instead of having a bank that spans a fixed address range, doing some weird things with additional costs of hardware to do it differently. So there are DIMMs or soldered memory or whatever. There are memory banks that each bank has a fixed physical address range. It has a start address, it has size, and in the NUMA systems, a bank belongs to a NUMA node. And on systems that support memory hot plug, a bank can be removed or inserted. There could be an empty slot that is not populated at boot, but it then can be populated during system runtime. Ted, would you like me to answer questions as I see them, or we postpone everything to the end?
It's totally up to you which you prefer. If you think you're would like to answer questions as you go, that's great. If you think you're running out of time, you can feel free to defer questions towards the end.
I think I'll defer questions for the end unless something jumps with the raised hand and want to ask immediately. Thanks. So back to the things. We have a collection of. To recap, we have a collection of continuous memory banks. Every bank has a physical address, it has its size. It might have a particular NUMA node it belongs to. It might be plugged unplugged at system runtime. Then what kernel says is actually not real physical layout, but it's what firmware tells it. So all the architectures have a mechanism to communicate with firmware what are the physical memory extents. Most of the time it boils down to some sort of defining physical memory address ranges. Firmware also tells what ranges are already used by it and shouldn't be touched by the kernel. On some architectures, there's also a requirement that some areas won't be even part of the kernel page tables because it may cause a CPU to go nuts about aliased mappings of the same memory. There could be memory that it's unusable because of hardware errors and so on. And all this information gets into the kernel with the either device tree or ECPI or E820, EFI ECPI, or whatever other bootloader mechanism there for a particular architectures. Now, one interesting thing is that there could be two entirely different ways of defining what memory is usable and what memory is not usable. x86 and E820 define usable memory and unusable memory in a way that the ranges do not intersect one with another, which means x86 has a notion of usable memory that comes as a system RAM type, and all the other types that can be actually used by kernel have different types defined by EFI, CPI, whatever standard you name. But these reserved ranges never intersect with the system memory ranges. On the other side, there is device tree and the other bootloader mechanisms that just say, okay, here I have memory, and here I have a reserved memory that I've cut off that memory I've given you, or maybe I even reserved memories that doesn't exist at all, but I still want it reserved because there are configurations which has this memory populated, or there may be hot block, and that memory would be populated at some later point. This point created a lot of confusion in how memblock is integrated in x86 in the first place. And I still see consequences of that confusion. So my thoughts about how we would model the physical memory is pretty much what we have in that way or another in either resource tree or memblock or memory blocks of the memory hot plug. We have a representation of memory bank that has an address range. It has some attributes like hot pluggable that maybe it cannot be mapped into the kernel address space. It may be online, offline in some particular mode, or it could have a NUMA node assignment in the systems that support it. And for memory hot plug, then we need a struct device to have user ability to see the memory bank in sysfs. And I don't think it will go away soon because we don't break user space. Except the memory bank, which kind of abstracts the physical memory bank, we need some representation of the memory that already busy by the time kernel starts. It also has address range. It also has some attributes like can it be mapped or not? I'm not sure it's required here, but probably. Was it reserved by firmware? Was it unusable because of hardware errors? Or it was allocated during early boot by for instance, memblock? And it also has it also should have attributes that directly correspond to what the architecture see, like ACPI types or EFI types, and depending on other architectures, there may be other things that the architecture would like to put it. So shortly, it would be some kind of architecture flux in that structure. I don't know, maybe it should also have a NUMA node assignment, but I'm not sure about it at the moment. And to wrap it all, we need some collection that glues a memory bank, collection data structure that glues memory bank and reserved memory representations. And it could be a tree, it could be X-array, it could be just resizable array like memblock. So we can choose, I think there are 3 possible ways to move forward with this representation. One is to start a completely new model, which doesn't look like really bright idea to me. So we'll add the fourth point of synchronization to what we already have. And it would be too revolutionary rather than evolutionary. It's not the way we do things usually. So which leaves us with two main candidates for the implementation. One is the resource tree and system RAM sub-hierarchy in it. And another one is a memblock that already has that both of them somehow represent physical memory, and both of them have very similar structures like start and blocks and flags and so on. And obviously, because I'm working on memblock, I tend to like memblock more. But anyway, I think these are more of objective reasons why resource tree is not very suitable for representing physical memory. First, system RAM is a subtree of it's a subtree of IOMM resource, and I don't know, it makes me shiver. The bits, the flags in the resource struct resource do not really correspond to what physical memory needs. They're more of what IO and memory mapped IO need. The struct resource is not supported on all architectures, in the sense that not all architectures register a system RAM resource because they don't have exec support, so they never had the need for system RAM resource. Whenever you'd like to do some query about whether an address is in physical memory, whether it's busy or free, the traversal would also include the whole bunch of actual IO memory, which can be quite a lot on the systems with lots of devices. And I think that having exactly one owner of a particular range is really strict requirement for the physical memory representation. Now, why I think memblock is the better option. So first of all, it's supported by all architectures. Everything uses memblock as the boot time representation for initialization of the page allocator. Memblock has ability to add memory and reserve memory from time zero, from the very beginning of the kernel, because it's static array that's always available, well, up to some reasonable limits. At the moment, we have ability even to define a amount of per architecture reservations at the boot time. Since it's an ordered array, it has a comparable performance with the resource tree. And the memblock region already has most of the necessary bits. So there are only small additions that required to memblock data structures and flags to make it more complete a model of the physical memory. There are still some issues that need to be addressed. For instance, memblock has no locking because most of the time it runs before threading is available, so there is no concurrency whenever memblock is used. At the moment, we have theoretical arrays in memory hot plug on ARM or on PowerPC that will add two banks simultaneously, and will require simultaneous memblock add, and that may go wrong. And now there is an issue that memblock remove may fail, and there are almost no failure checking on the memory hot unplug path. There is also perception that memblock is an allocator that replaced bootmem. I even thought about sending a patch that will rename memblock allocator functions back to bootmem allocator functions, but probably it's too much. It would be too much, and well, maybe next 1st of April I'll do it. And there is there are some issues in how x86 uses memblock. I'm trying slowly to move it. I'm trying to move slowly to solve them, but it will take some time at least. So the first thing I wanted to do is to move the registration of system RAM resources to memblock for all architectures that actually traverse memblock data structures and use them to register a system RAM resources. It didn't went too well, but I'm hoping I'll to resend this with all the feedback addressed. I'm thinking of adding flags to differentiate between reserved regions, so it will be known what exactly reserved made the reservation. Was it kernel, firmware, and so on. And I'm working on creating a clearer boundary between the memory representation and the low-level APIs like memblock add, memblock remove, to the allocator part that actually does low boot time memory allocations. The next steps I was thinking of are making memblock remove resilient, making memblock remove essentially void that so that it won't fail. To be honest, I don't know yet how exactly am I going to do this, but it will be done at some point, I think. There are still some inconsistencies between how architectures treat different pieces of memblock and the generic code does. And there is also a need to remove architecture-specific data and code that represents exactly the same things, probably in a different way. I'm not sure it's even possible, but at least some of the data may be recreated from memblock, or memblock may be recreated from that data, depending on the state. But the major point, the whole bits here must be in sync, and at the moment they are not necessarily up. And sometime in the far future, probably we'll have the only representation of the physical memories that will be used to as a backend store for current APIs like sysfs and proc-iomem, and we could enable ArchKeep memblock on architectures that support memory hot plug, and remove the need for updating the memory state from the memory hot plug, but rather do it one time with, for instance, memblock add, and the entire surrounding representations will be updated automatically. So now it's time for a bit of discussion. What am I missing? So I'll maybe try to address the questions first. So first question from Charlene. Quick question. Should I read them? Quick question, probably orthogonal. How does hot plan really work? One needs a physically continuous allocation of struct page for that given physical address. Yes. Hot plug, there is a document, I think David Hildebrand written a while ago, that covers how hot plug works from the user perspective. I can't say I'm really familiar with the internal workings, but whenever there is a bank inserted and there is, for instance, on x86 an SCPI event that causes creation of the memory map and then aligning of that memory, I'm not sure about particular order, so please take a look at memory hot plug documentation in the documentation. Liam, could some indication that VM memory isn't actually real worth having? Would we want to be treated differently in some way? Liam, I'm sorry, I can't say I understand the question. If you don't mind to turn on audio.
Hi. Hello. Hi. So I was thinking like you're showing how you were going to represent the memory, and I was wondering if VMs, if VMs indicate that they are VMs in the memory blocks, then we would know that it could be hot plugged, or it could be maybe transferred to another machine or migrated or something. And I was wondering if that would be worth having or not.
Maybe. Well, at the moment we have all the kinds of ballooning, but they do not really remove physical memory. Virtual memory is the closest thing. It already does hot plug, hot unplug. So whenever there is virtual memory on the virtual machine, it just goes via the hot plug pass.
And I'll also mention the page VMs will get data managed in page levels really, and this stuff is really much coarser granularity than that. So I don't think page level stuff really works well in these representations in general. So this is the right data structure.
Dave, I didn't mention page level. Maybe can you repeat your remark, Dave?
Well, I was just mentioning that when we talk about virtual machines and physical memory, so this really is representation of what the kernel sees as physical memory. So what you were talking about here the whole time was about the guest physical space, not about the bare metal host physical space. And the problem is that the translations between the two will be broken really at the page level. And all the data structures you talked about today, if we had, hundreds of gigabytes of memory and every other page in that hundreds of gigabytes of space was, either present or not, which the, hypervisor could do. These data structures really don't work well for that. So just saying, this is really representing the guest physical space. This really is not representing the host physical space in any way, shape, or form. Everything you talked about today. I hope that makes sense.
Okay. A question from Matthew. Local memory presents physical address space. There is no problem with having system RAM separate from that, but failing to report your system RAM program memory is architecture vulnerable to multi-area resources. Matthew, I'm not saying system RAM should not be reported in proc IOM, but maybe I don't really understand the question. Do you mean that if you don't have system RAM in proc IOM, then you could map PCI resource?
Yeah, so this was while you were talking about whether we should be using the resource tree or whether we should have memblock as the fundamental representation of how memory is laid out. It's not a problem to me to think that that we should have two separate trees. It does make sense to an extent to have a separate representation of things to actual memory and things which are not memory. But what we do need to be careful of is that things which are represented our memory ranges do show up in proc IOM. So the architectures which aren't adding system RAM to proc IOM are potentially buggy because our resource allocators, like if you're doing PCI bar allocation, particularly for a root bridge, they need to know to not overlap with system RAM. We've had some fun bugs with that in the past.
I'm not sure these architectures support PCI to start with. They might not, but I think the system RAM sub-hierarchy added to the program memory entirely independent of the root bridge bars. And I did some archaeology. It was solely for purposes of kexec, so that user space could see where the system memory is from at some point in proc. I think there was no sysfs at that point. So it was added not for purpose of proper allocation of IO resources, but for purposes of kexec and visibility of system RAM. Even not the system RAM itself, even more of where the first kernel before kexec lives and what memory is occupied by it.
I think that might depend on your architecture. I know that on PA risk we did add the system RAM allocation to proc.io man because we needed to know what address ranges were free for the root bars, for the root bridges to start occupying.
But anyway, we are not going away from system RAM sub-hierarchy in the resource tree. The question is whether each architecture has to generate it itself, or it can be automatically created from the information we already have in MapBlock anyway.
Oh, I'm all for populating that from shared code. There's no reason for that to be done by the architecture.
And we anyway have to keep it for quite a long time because it's an ABI, right? So. Are there more questions? Anybody? Comments? So probably I can give you 3 minutes back. Thanks, everybody.
All right, thanks, Mike. So as I mentioned, I will be taking the shared notes in just a little while. I see there are still people who are conversing on the shared notes, but in a couple of minutes in the middle of the break, I will be clearing the shared notes and copying the questions and comments that people had written during this session into the Google Drive doc, which is at the beginning of the shared notes, for people to look at and to archive that. So thanks again, Mike, and we will be on break for another 15 minutes before we start again with the Rust for Linux talk. What was it? Yeah. Miguel, are you going to need help uploading your slides into BBB or the Linux Plumbers conference website?
I just did the Indico one. And here, if you give me, please, the presenter rights, I can upload them.
Okay, great. I will give you presenter rights right now.
Thank you.
We'll be starting in about 2 or 3 minutes at the top of the hour. So thanks for uploading your slides.
I don't see them here for some reason. It's not showing them. If you are seeing them, I will rejoin.
Okay. I can see your slides. Just one word of note, and I'll repeat it at the top of the hour to make sure anyone joining late hears it. The chat has been unhappy, if folks haven't noticed. I think it's getting better, but it's still taking better than a minute for folks to connect to the chat server. So what we've been doing today is using the shared notes for questions. Just add your name in parentheses before you add a question to the shared notes. And that's our workaround. The Linux Plumbers organizers are frantically trying to figure out how to make matrix scale. Apparently having 1,000+ people connect to a single threaded Python server doesn't work all that well. So please bear with us, and we'll beginning. I'll begin just at the top of the hour.
Let me rejoin to see if I see my own slides. 1 second.
Ed, we can't see the slides. It's not just Michael.
Okay.
Perhaps I will switch again. Let me see. Now I can see them. Can you see them?
I can see them, thanks.
Yeah. I don't know. When I closed the upload dialog, somehow it looked like it was switching the slides, but it didn't put anything. Sorry, the sun is killing me. Yeah, it's too dark. Oh well. I will do my best not to get blind. Yeah, I'm connected in the Matrix chat, so perhaps I can see the questions in the chat. But yeah, I will take a look at the shared notes mostly.
Great. We're at the top of the hour, so let's get started. For folks who may have just joined us, I know today, Monday, has been sort of Rust Day, so we've had Rust talks in the referee track as well. What we've been doing today on the Kernel Summit track, because the Matrix server has gotten a little overloaded, has been to primarily relied on the shared notes for people to ask questions, and then the shared notes are being archived in that linked Google Drive doc. So if the presenter wasn't able to get to all the questions that were asked, hopefully he'll be able to check the Google Drive notes and then maybe answer questions there for anything that we're not able to get to today. Since this is the last session, I'd like to thank all of the sponsors for the Linux Plumbers Conference. And this includes Facebook, IBM, AWS, ARM, Microsoft, and silver sponsors Red Hat, Netflix. Oh, sorry, AWS is a silver sponsor, and Collabora as the speaker gift sponsor, and VMware as the t-shirt sponsor, and Linux Foundation, who's been providing us with conference services. I'd also like to especially call out thanks to members of the Linux Plumbers Conference who have been working to put together a completely open source virtual conference infrastructure. They did that last year, trying to improve things this year. Couple of rough spots, but let me assure you, they've been working super hard on it, and I'm eternally grateful for all of their efforts. So again, thanks to all of our sponsors and to the LPC Planning Committee. And with that, I'll turn things over to Miguel, who's going to be talking about Rust for the Linux kernel.
Thank you, Theo. Yeah, so thanks for coming. Thanks also for having me in the Kernel Summit. I know we had like Theo was saying, a Rust Monday, and we had this talk is a bit more a follow-up of the previous talk we had in the referee track, where I discussed a bit Rust in general, like for user space, for Linux in general, the Linux ecosystem, and this one is the one focused on the kernel. We would like to have probably discussion. I don't know how much time, so if you want to have discussion, we can stop the talk at any moment and we can discuss, and that's completely fine. I will try to go quick on the slides to leave as much time as possible to discussion. But for those of you that were not in the first talk, I am going to try to give like a very quick right now summary of the other talk, basically basically answering the question of why we want Rust in the Linux kernel first, and then we will talk about a bit. Couple of examples of how things work or a couple of diagrams on how things work currently in the project, and then we can have the discussion if you want. So first of all, I want to give some credits first to Rust for being like a new approach or bringing some new ideas to the system programming languages field. To kernel maintainers for having been patient and open-minded so far with us, or at least most of them, and everyone that has helped the project in one way or another. It's too many people. I can thank, of course, Wilson and Alex, which are the maintainers like me of the project, but there is also so many more people that have helped, both from the from the kernel as well as external people from the Rust team, contributors to the compiler, etc. So thanks a lot. With that, since a few days ago was the anniversary of Linux, the kernel in this case, it's 30 years that Linux has been around in the world. And it's also for standard C as well. It's more or less 30 years, so they go a bit together. Of course, not just Linux, also Unix goes with CC as well. And also in the kernel, we don't use standard C as such. But anyhow, it was a nice. It's a nice coincidence that it's more or less they are more or less the same age. So, talking about C and the kernel, it has not been always like a smooth story or trajectory, because as you know, well, we use extension, we have had our differences on the memory model, etc., etc. So there is some things that we could discuss about the kernel and C. And here today we are trying to bring a new language to the kernel, right? We are trying to see whether a new language could be good enough, or the value proposition be good enough to overcome the costs that adding a new language to the kernel has. So is this an easy task? So Linus Torvalds was asked this a few years ago. Do you see any language except C which is suitable for development of operating systems? And he answered, I have yet to see a language that comes even close to C. So with this sentence, at least some years ago, it was this was like a pipe dream, let's say, like something that would be very hard to achieve for good reason. I mean, if C is good enough, why do we want something else? So why is actually good C for the kernel, or for in general development or operating system, which is what was designed for, right? So Torvalds gave some reasons, which is one is that C generates fast code, which we all know about. It's low level, so we can map easily in our heads what is the assembly going to look like, at least if it is not going to get vectorized and things like that. It's also a simple language compared to, for example, C++ or even Rust. So it's a simple language to understand and to build a compiler for. And if it's the domain, because well, it was designed for that. So of course, if it's the domain of writing kernels and other low-level tools. But there is a key problem with C, which is, and I will be very quick because this is basically what we talk about in the first talk, and I will go through it very quickly. It's undefined behavior, as you know, all know. And what Rust offers, and I'm not going to explain undefined behavior here in order to have time for discussion, but what Rust offers is no undefined behavior. And this includes memory safety, type safety, etc. In particular, when we discuss, and I may put this here because I think it's important to clarify this from the get-go, safety in Rust, it doesn't mean safety in some safety critical sense or anything like that, is no undefined behavior when coming from C. So if you come from C, you know what undefined behavior is. Rust basically says there is no undefined behavior in the safe subset of Rust. That is exactly what they mean, and we will see a couple of examples. And it's not related at all with safety critical. So for example, if you have worked on airborne applications or trains or cars, things that may kill people or they may injure or may have some impact on actual safety as in functional safety, this is not related to that. So safety in Rust is not related to safety critical. Functional safety is more about requirements, traceability, independence of quality assurance, etc., etc. So it's completely different. You can write safety critical software in both C, also probably soon in Rust. There will be companies using it, ADA, etc., etc. So it's different and it's not related to safety critical. With that out of the way, why we say that avoiding undefined behavior is important? Because yes, C has that issue in between quotes. He has undefined behavior. Is basically comes from the design of the language. It's not so much a problem. It's how the language is designed and how it's supposed to be used. Like it was designed as at least in the beginning, as a high-level assembler, if you may. So why is important avoiding undefined behavior? And the reason is simply that there is 70% of the vulnerabilities in C and C++ projects come from undefined behavior, basically from memory safety, most of them. This, I have some, for this, I have some slides. We saw some data on this. So if you want more information, you can read this link. You can also see the other talk and in the recordings. So you have to trust me on this so that we can go a bit quick here. So someone may say, okay, fine, undefined behavior is an issue, it's 70% of the vulnerabilities, and safe Rust does not have it. But does that mean that using Rust actually helps with that? Because there are several questions that someone may ask. For example, well, if you have to use sometimes unsafe Rust, or a lot of times you have to use unsafe Rust, then perhaps it doesn't really matter. I mean, even if some subset of it has undefined behavior, does not have undefined behavior, if you have to write a lot of unsafe Rust, then perhaps the number of vulnerabilities is the same, right? Or somebody may ask, or may think, well, yes, it may not have the safe subset undefined behavior, but if this language is so complex that the programmer has to put more effort or the programmer may make more mistakes per line of code, for example, then perhaps there are more vulnerabilities, even if they don't come from memory safety, perhaps they come from other sources, and then they offset each other, basically. So does it help? And in the first talk, we basically I made a poll on seeing if folks were going to guess this plot, basically. So look at the security Patchwork project, the red part of the plot. This comes from is derived from this blog, which I explained on the other talk. But basically, from a set of projects, I didn't pick them, I didn't anything, and please take this with a grain of salt, because what I did is from the spreadsheet that they published with all the security bugs and the bugs that they found, I just took the major language per project, I filled a table with the language, and then I plotted the numbers. So the average number of bugs and security and non-security bugs per project. And this is what it is. It's not normalized by, for example, lines of code or anything like that. So again, it's just a first order approximation, but I think the approximation is good enough because as you see here, there is no red part in the Rust column. So basically there were 0 parts in this project, which is basically the Google open source Fasten project, has 0, the fastest encounters 0 vulnerabilities on the Rust code. Of course, the Rust projects may be too few, so not enough samples perhaps. It may be that there are many factors that can get into this, but again, as a first order approximation, I thought, okay, 0, because when I saw the spreadsheet, I was not looking for these numbers. I saw that it was 0. Basically, I saw some names that projects I recognized, and I said, okay, all of them are 0. Let's see all of them. So I went one by one, I created the table, and I found this, which I thought it was amazing. Of course, Rust still has other bugs, and of course, there are still bugs and vulnerabilities in Rust, even if this data does not found anything. But I still think, again, I think it's a nice summary of that. So what else, apart from the non-defined behavior property, which is the key, and this is why we want it in the kernel. This is basically the key property of Rust. And other languages, how the system programming languages that we could use in the kernel may or may not have this property. Some of them have similar properties, or they have a bit more lax properties, but the undefined behavior is the one that we really want. Now, Rust also offers other things as well. So it's important that we give like a very quick overview of that. So Rust offers, it's like you can say it's like a cleanup C++. It offers a stricter type system. It offers modules and visibility, generics, lifetime, sum types, a lot of things that we can take advantage in the kernel. So these are all things that actually I think the things I will put into the slides are things that I think are useful for the kernel, not just Rust in general. Then there is the free standard library, so the one for kernels, operating systems, as you know, bare bones, etc., embedded. I will answer the question. Francois, in your security comparison of languages, do you have data on number of lines of code? No, I didn't go into lines of code for each project of that blog. Basically, the blog was something I saw the numbers, I saw that it was everything zero, there was no vulnerability on the Rust side, and I said, okay, it's very interesting because that plot is from 3 weeks ago. So, and includes major projects and smaller projects, so it's a bit of everything. It's in total is 100 projects plus. I encourage you to look into their talk, because I also ask folks, before showing the plot, I asked them, before showing the column of Rust, I asked them how many vulnerabilities you think the Rust column will bar, the Rust bar will have, and half of the attendees said 0 to 2, and they were quite correct. Some of them said no, a lot, like C, C++, others said like Go and Python. So it was very nice. So the free standard library, as I was saying, I will try to go even quicker. It's basically the standard library, not the high level things or the things that depend on an operating system, but things that can be used without our operating system. These are things that we use in the kernel in Trust for Linux. And things like, for example, result and option are very important, because these are a way to handle error cases. Let's say the result is a way to handle error cases, and that is used by every single Rust project. So it's a type that is basically taking care of all the error handling, and everyone uses it. So no more taking care of what is an int, whether the return code is higher than 0, less than 0, equal to 0, whether if it's a Boolean, whether it's true or false, which is the error case, which is the OK case, etc. So there are some things that we use and are interesting. In particular, also the checked, saturated, and wrapping inter-arithmetic primitives are also nice to have in the kernel. And we use in a couple of places we use already them. And there is tooling for the kernel. We already use a lot of this tooling. There is a documentation generator, a static analyzer, a linter, a formatter, etc. There is a lot of things. These ones are the ones we use. And of course, you can use GDB, LLB, etc. with the usual tools. Well, background in the case of user space, but the point is you can still use the normal tools with Rust code. So what is the catch? Rust as a language cannot model everything. So sometimes unsafe code is required, but much less than you may think, even in a kernel. So even in a kernel, it's very, we can have drivers that are completely safe code or almost completely safe code to the point of 99% of the code is possible to have, even when you are reading arbitrary addresses in memory, because we can take a register map and have the register map compute the addresses statically, let's say. So if we know the addresses on compile time, we know them, then we can wrap those things into functions that do not allow you to compute any offset, basically. So the offset is pre-computed, let's say, or is hidden in the safe function. So there is no computing on any offset in the caller and then calling, for example, read B or write B, right, in the kernel. So instead of that, we will provide functions that have the offset already in the inside. So while unsafe code sometimes required, it's less than you may imagine initially. There is more information to provide to the compiler in order to prevent some kinds of undefined behavior. This means a more complex language, so that's a catch, and it's more complex than C. There is some extra runtime checks in some cases, not in all cases. It depends on what kind of thing the compiler is trying to check. For example, out of bounds The compiler may be able, if you are using, for example, an iterator, or you are using something that the compiler knows what are the bounds, and you are not doing any like arbitrary computation of the index, then it doesn't need to check for the bounds, for example. So it depends. It depends. But even if it's potentially expensive in some cases, please recall that we have unsafe code. So this means you may write the majority of your code in safe code, and then even if you need in some whole loop, you need really some more performance in some particular case, we can use a line of unsafe code, for example, to perform an access or things like that, unchecked. Basically, they call it unchecked in Rust. So there is no check on the bounds, for example. And of course, the major one, and for the kernel, I think this is the most important, is an extra language to learn. So it's some logistics and a maintenance burden. This is basically what we want to discuss today. Basically, Rust offers us some advantages, which I think are very important. Quite a few kernel maintainers have told us that they think is interesting, but of course, the key here is the cost. So there are two questions that we need to discuss later, which is, or during the LPC conference, which is one is, do we actually want these features? Do we want this no undefined behavior language? And if we want, then how we are going to create a process or create some way to have a transition period to integrate Rust and give some time to kernel maintainers to learn the language. Then, if you remember the slide from a few slides ago, we have what Torvalds was saying about C, and this is a comparison with Rust. So Rust, does it generate fast code? Yes. It's low level sometimes. Sometimes you can map easily what the assembly is going to look like. Sometimes you don't. You cannot map it easily because it depends. It depends on the kind of code you are writing. For example, if you change some iterators and things like that, it may happen that it's not easy to follow. It's simple, not really. This is a disadvantage, as we already said. And if it's domain, I think so, because Rust was partially, or at least from my point of view, it was designed to replace C++ and C. So I think it fits domain and is used already in some projects that we saw in the other talk that use Rust already for this purpose. So it's an easy task, maybe, because if you see here, Torvalds said this before Rust was a thing, or at least perhaps it was in the design phase, but the point is, Torvalds said this before. So I know this is a bit of a fun slide. I'm not meaning to say anything particular, it's just for fun. But the idea is, when Torvalds or other people, not just Torvalds, were thinking about C and what could be done in the kernel or other languages like C++, etc., Rust was not there. It's quite new, but it's not as new as some people think. So I think it deserves a chance to be reviewed, to get into the kernel. And I think it's about the time that is right for us to get into the kernel. If you asked me 2 years ago, I would have said it's perhaps too early. Or 3 years ago. If you ask me now, I think it's basically the right time we can pick up Rust for the kernel. And of course, compare, for example, with C++. C++ does not offer that key advantage. So if you compare it with other languages like C++, it doesn't offer the key advantage that Rust does. So there is some trade-offs there. So some example, just to try to make it more concrete, and since I had to go very, very fast with that introduction, some examples where Rust helps. This is taken from the Cangrejo talk that we had last week. Some examples. So this is Compiler Explorer, many of you know. In the top side, you see Rust. In the bottom side, in the bottom half, you see C. Basically, it's equivalent code, or less. And what we see here is in the C side, which I am pointing at, we have a malloc, and then if the malloc allocation fails, we abort the program, and we write some number, and then we have a double free. So in the case of C, of course, several things may happen depending on your optimization, depending on your compiler, etc., etc. In the case of Rust, as we see here, a double free drop basically would run the destructor, let's say, of this box type. A box is like a pointer, a unique pointer in C++. An allocation, if you want, like a box where you put an object. So if you try to drop the object twice, then you get an error, compile time error. But this is a very simple example, like the most basic example of how Rust prevents a double free. Of course, we cannot explain here all the mechanisms of how Rust does it in the general case, but what I wanted to show, is that this is actually prevented. let me see the questions. What are the areas of the kernel that would make good candidates for Rust? Full disclosure, I played with Rust and made it to owner. Sorry, the chat is 15 to ownerships and compiled Rust in Git. I like some aspects of it. So good candidates, it depends. If you are asking, for example, from the perspective of the process that we want to discuss later, from the perspective of the process, I would say drivers are the easiest in the sense that if a kernel maintainer is more or less okay with having Rust, or basically is on board with Rust and wants to have Rust on their subsystem, then drivers are like the key, not the key, sorry, like the easiest way to put Rust, because we can write them as long as we can write them with mostly safe Rust, then that's the key, because what we want is safe drivers, so that we don't have to be always reviewing and always re-reviewing whether something may have a vulnerability or not, whether we are doing a double free, etc. If you are asking in general, not just like where Rust makes for good code in the kernel, I think everywhere. And this is not, I know it looks like exaggerating, but with the examples I am going to give a bit later, you will see that it actually offers some advantages in all kinds of code, basically, compared to C. In this case, we avoid allocation errors. How does one handle allocation errors without panicking in Rust? So we in the kernel we have we discussed it with the upstream Rust, and we have now fallible allocations in the library. Okay, so the allocations, while this one is not fallible, the ones that we use in the kernel are. And upstream Rust is adding support for this. And we actually upstreamed some of the functions that we needed. And we have some more functions that are fallible allocations in the kernel. And we hope that upstream keeps taking these functions so that we don't need to, we will get into that a bit later. So this is double free. Let me go a bit forward. This is another example. I will not get into this, but basically, as you can see here in C, if you follow my pointer, this is a use after free. We are using this. The program says the output is 0, but it could be different output, for example, a seg fault or a 42, depending on your optimization, your compiler, etc. And in Rust, if you try to do a use after free like this, you get, again, another compilation error. Another example, for example, this is type confusion, or basically using a union with the member that is not the one that is correct. It's not undefined behavior in C, unless I'm completely mistaken now. In C++, it is undefined behavior. But the point is that even if it is not undefined behavior in C, Rust does not allow that with some types, with enums. Rust also has the unsafe equivalent, which is the union, like same as C, where you have to prove that you are not mixing basically reading one member that was not the active member of the struct, of the union, sorry. So there are also other features that I'm trying to show here that actually prevent this at compile time. And again, here is a compile time error. More things, for example. This is more, rather than an invalid code, this is more an example of like coming back to the question that Shua was asking, areas of Rust that the kernel can help. For example, this one. So see here, this is, sorry, in the top side, I put this, my mistake, I put C in the top. So here we have these two functions in C. And in the top one, get some data, we see that we have to put some comments, right? We have to put some comments in order to explain, for example, what is the success case? So what is going to happen when the success is, when the function is successful? So for example, result is going to be written here. So it's the output parameter. An int, and this return value is just whether there was an error or not. And perhaps what error, perhaps. So we need comments to explain this, because the type, the signature, does not tell us what is how that function works. While in Rust, and I'm hiding here some code because otherwise it gets a bit messy, but it's just because in order to put the code in Compiler Explorer and have it compile, I'm using external function. But forget about that, it's not important, for example. Here, we have the same function, but as you see here, this takes no parameter, so there is no output parameter in this case. And it returns a type called result, which I mentioned in the free standard, standard library in the slide a few moments ago. So here it means this function returns a result, so it can fail or not. It's a fallible function, so this already tells us it's fallible. And second, it tells us, this type already tells us whether it's an OK or an error. So it already distinguishes those two possibilities, and you cannot make a mistake mixing them up. So there is no possibility of, for example, that somebody changes that the error is not 0 now, it's a negative value, and now the success is a negative value. So this cannot happen in Rust. And it also allows us to put everything in the return type, because the result contains both the error case and the success case. So for example, if we want to return a number, like the int out parameter here, this goes in the first generic parameter, if you want. And the second one is like the empty type, because we don't want to have we don't want to return any error. Basically, we don't want to return any information on if there is an error. So this already, with only the signature, I can already tell everything that was being written here in the comments. That's one of the things that, to show a very simple example that shows some features that allows us to really improve the code in the kernel, even without taking into account whether it's a subsystem or a driver or anything like that. There's a question, will type encodings be discouraged? For example, okay, I will let you finish the question. I will read later. So this is an example of result, which is an example of a sum type. Now let's see how do we build an abstraction. So we build an abstraction like this, which this came in Cangrejo, so I wanted to have a couple of slides on this. So imagine that we are in the kernel. Just imagine that we are in the kernel and we have some bindings here. So we have two functions, one that gets a pointer and one that that uses a pointer to perform some prints. So if you were to use this in C, calling these functions, you could let me put it this way. In C, there is no notion of safe or unsafe. So we have to, in Rust, we have to abstract this code in a way that there is no way we can trigger, the external user can trigger undefined behavior, right? So what we would do in the kernel? In the kernel, you would have something like this. Not just in the kernel, in other projects as well, but the point here is having something like the kernel. So you would have a file somewhere that is abstraction code. You have a module, ignore this, it doesn't really matter, and you have extract. So the pointer, instead of using the pointer in your function directly, what we will create and allowing, for example, drivers to call this, we disallow this, and instead of doing that, we have abstract that contains the pointer and contains it privately. So others, the people outside this code, this file, this module, or people outside that cannot touch this PTR. So then we have some methods, and this is a constructor, and this is the function, like we basically another function that does something with the pointer. And you see here some safety comments, and these are comments basically that prove that manually prove. These are like so the things that the compiler cannot check, like for example, calling a C function cannot be checked. We have a coding guideline in the kernel that requires us to put why this is safe. So the proof, the manual proof that why it's safe. So for example, the get pointer is always safe to call. That's the trivial case, so we call it, that's fine. And we get a pointer and we return the structure to the call. So for example, to a driver will be calling this function to get a foo, okay? And then we want to do something with the foo, and we can call this method. And calling this method, calling use pointer, we need to prove, because use pointer will access the pointer. So we need to prove that using the pointer is not going to, so the pointer needs to be valid when we make that call. So for doing that, we pass the pointer we have. But why this is safe? Because why somebody cannot modify that? And that's what so this is the example, the working example. I will go to the not working example because perhaps this is easier. So you see here, this is the driver, this will be like some driver. And in the driver, we create this object, as I was saying. And then we try to modify the pointer. We try to put some random address there. And then we call the function. And this will break because it would call the C function eventually, passing here, and it would pass a broken pointer. You see here, there is no unsafe. So in the driver, there will be no unsafe code. And we get a compile time error because we are trying to access a private field. So for example, visibility in Rust is key to provide safety guarantees and providing safe interface. So this is a trivial example of how we would create a safe abstraction for a driver. And of course, the working code will be this. So if you don't modify that pointer, then it will work. And the compiler wouldn't complain, and you have the assembly here that, as you see, is what you expect, basically. So you basically have a call to the get pointer, and then a jump, what is optimized to a jump to use the pointer. In this, will type encodings be discouraged? For example, using the power check to enforce this term for context switching in KVM. Type encodings, in what sense you mean? You can perhaps ask, or we go back later. So right now, Rust is a client of the C APIs. So we are not trying to like rewrite the kernel in Rust, let's say. Okay, we are not trying to rewrite that. What we are using is putting abstractions on top of that. So for example, we cannot play things we cannot try to work with the workload checker across C. That doesn't make sense. What we do is create an abstraction on the Rust side, and then we have the workload checker work there. So for example, if you mean by type encodings, type wrappers perhaps of the C APIs, then yes, we would use them. So not discourage, quite the opposite. But I'm not sure I understood the question correctly. Yeah, so let's go ahead. So Rust support in the kernel, this is very briefly how it works right now. It's open, still the design is open. There is no need for basically to, what to say, sorry. Basically everything that you see here could change in the sense that we are not saying this is the best solution. We are saying that this is the best solution we could find, but we could change this. But at least to give you some rough idea of how it works. So there is two trees here, the Rust tree and the Linux tree. This is the standard library, what we care about. We only use core and alloc, which are the library that we need. We have in the kernel right now, but this will be removed, a copy of the upstream Rust alloc crate because we need those new functions that we needed to add to the standard library. As soon as upstream gets those things, publishes a new release, then we can remove the alloc crate. Although I wouldn't do it right away, even if we have all the support we need, because we still want to have probably modify some things or add a new function. So it's better if we leave the alloc crate for a while inside the kernel, so we have more flexibility. Then we have here the kernel crate, and I saw online some people getting confused about the kernel crate. The kernel crate doesn't mean that we are rebuilding the kernel in Rust. The kernel crate means it's the abstractions for the kernel. Okay, so it's the abstractions of the C APIs. It's not that we are building a new kernel in the kernel crate. Then we have the binding, which is a tool that creates automatically the bindings for the C headers. So it parses the C headers and creates automatically Rust functions for those, so that it's easy to maintain. We don't need to maintain both in both sides. There is some limitations, of course. For example, C macros don't make sense to complex C macros. I mean, like not just a constant, but a complex macro that does something in C code. It doesn't make sense to use that to try to expand that in the Rust side, right? Yeah, that's basically it. I mean, the most important part, perhaps, to understand from a kernel maintainer's perspective, is this. So we have here three parts. One is at the right side, we have include binding, which, as I just said, this will be the bindings to the C API. So at the right, even more at the right, will be the C side of the kernel. Then we have the kernel crate, which are the abstractions, as I write here, of the different subsystems. This could be a split. This could be different crates. The crate is a compilation unit, basically, in Rust. It's the translation unit in Rust, but doesn't really matter. We can change this. We can split it. It depends. The design of this is not. So it's not important that we put or not things on the kernel crate. What is important is the other thing, which is that the driver here will only ever call safe abstractions through this crate or set of crates. And the key is that you cannot call C functions directly from a driver. And while this may seem restrictive, is the key of having most of the code in Rust in the kernel be safe. Because if we allow this to work like this, then we will end up, it's my bet, that we will end up with drivers calling unsafe functions in C everywhere. I'm not taking the time to build an abstraction. So if we pay the cost of building the abstraction first, then we can have all the drivers using safe abstraction. And this is what we have been doing. Especially, for example, Wetson has been working on for example, in NVMe, et cetera, to create all the abstraction necessary to have some of the drivers, right? So this is the key that drivers need to do. And this is the work that kernel maintainers would need to work on. So the hardest part of this work, basically for kernel maintainers, will be abstractions, because those are the ones that deal mostly with unsafe code. And unsafe code in Rust is the one that takes much more time to write and review, because it needs to, basically you need to know all the rules of unsafe Rust and also what your subsystem is doing. So for example, if you call a C function in the kernel, you really need to know what that C function is doing and what are the safety preconditions on that function. Otherwise, you cannot write the abstraction. So this is basically the hard work. And then the advantage is that then drivers or leaf modules or other modules, as long as we have this abstraction, then they are mostly or almost all or even all, I mean, it could be all safe code. So we can actually write drivers with 100% safe code. Of course, there may be exceptions, or there may be a driver that does something that requires some unsafe, or perhaps there is a hot loop that you want to use unsafe for performance just in one single place. But So can you speak to Rust ownership as they relate to kernel resource ownership model? We had this question a couple of times. Rust ownership is on the Rust side. So you can think of, you cannot play with lifetimes in the sense of getting the borrow checker to work on the C side. So what we do is we create some type, as we saw, a wrapper that has some constraints on it or some invariants, and those are the ones that will be checked by the borrow checker. For example, if we use references on the Rust side, those will be checked by the compiler. But we cannot. There is no meaning, so to speak, of trying to mix the lifetimes, so to speak, of the C side with the actual lifetimes in Rust, like the syntactical lifetimes of the borrow or the borrows, let's say. My limited experience with binding is that it does not create usable bindings, and you have to create them by hand. Is binding now working out of the box? Yes, for us. For most of the things, there are some things that you need opaque types, or you have to basically you have a list that perhaps some of them don't work, but it's really few of them. So far, what we have used has been quite nice. So we don't need to write manually the bindings. There are still some problems that we discussed also on the other track, which is, for example, binding uses like clang internally. So it doesn't use GCC. For example, if you build a GCC build kernel with Rust support enabled, and you are using binding there, then binding is parsing the C headers using libclan. So if clang somehow computes different memory layouts than GCC, for example, if GCC is used in the kernel with a plugin that randomizes addresses, then randomizes the order of members, then you have a problem there. So there is some things that we need to discuss, but I think this does Rust code effect make all just config almost config? I mean, while there is no Rust code in a subsystem, should I be concerned about an issue with binding? I could break compilation on it.
So Miguel, just briefly, I'd like to add to what you said about the ownership model. So one thing that we actually try to do is to, even though we, as Miguel said, we can't go across the languages to use the borrow checker, but we do have two aspects of this ownership. One is when we are using C things, then we wrap them in Rust abstractions. For example, everything that is ref counted in C is ref counted on the Rust side too, and ref counted in the way that is done automatically. When the thing goes out of scope, then we decrement the ref count. And you cannot clone a pointer, for example, without incrementing the ref count. So we do have these things for file and tasks and pretty much anything that is ref counted in C is also reflected in Rust. But we sort of do that manually, and we need to do that in each case, right? But the idea is that each time we find one of these that we need to interact with from Rust, we add these abstractions, and then this becomes available to everybody else that needs those same things. So this is one aspect, is when we are dealing with C objects when we are writing Rust code. We also have, in some cases, places where the C side is holding some state for us. For example, if you're implementing a file, drivers usually save this file, some file state in the private data field. Or when you have a driver, you have driver data. You have driver data on each device node, for example. So what we do in the Rust case is the abstraction that we create is such that the driver writers write something and then pass ownership to our wrappers. Our wrappers save this state on the C side, right? And then each time the C side tries to use that state, if it's like concurrent, for example, then we use the state shared. And then in the end, when you have a release sort of thing in the file operations, then ownership is transferred back to Rust. So we do have these manual instances where we try to make lifetimes mesh together between the two languages. But we do that manually. But the idea is that we do it manually once, and then everybody benefits from it on the Rust side. Yeah. Back to you, Miguel, for the other questions.
Thank you, Wilson. Yeah, like Wilson said, this we have to, of course, for example, for red counts, etc., we have to keep those matching and in sync with the kernel. But what I meant by the lifetimes, yes, is that we cannot use the borrow checker on the SQL. So everything we do is we have to use still the C APIs as they are supposed to be used. For example, if they expect a call here and you cannot call then a distractor, for example, or a deallocation in another place, we have to follow the rules of the C API. But what I meant is that we cannot try to use the borrow checker on the C side. So you cannot just try to do that. But we can take advantage, as Weston explained, of the borrow checker on the Rust side if we create abstractions. Which is the manual process that Weston is describing. And Mauro asked, does Rust code affect, so Mauro, binding, what we do is that currently we have a fixed list of headers that we create the C APIs for. So whenever somebody new is coming with a new header, it's the highest chance of breaking the thing, basically. If somebody changes headers, it can break the ones that are already in the list. Yes, it could break if there is an issue with binding. But yeah, we are using binding, and that's one of the problems, basically. We are relying on the tool to work properly. So if somebody changes that, probably it will need to add into the blacklist or into the denial list. It will need to add those manually, right? But it's up to use it, of course, on the right side, but you could also do it manually if binding doesn't work. So here are the supported architectures. I will go through that because it's not that important for discussion. And I wanted to leave discussion at least until the end of the hour. So there is several compilers. If you were in the referee track, it was explained what are the three alternatives, the main one that we have, and then we have GCC backend for the official frontend, and then there is the effort to put a new frontend completely from scratch on top of GCC. This is how the documentation looks. I will pass the slides while I try to read some of the questions. So this is how it looks. We can have also a discussion on whether we want to use this documentation or not. We think it's very, very important, or it's very nice to use this documentation because it knows the Rust code. It knows what are the things that are the feature of the language, and it puts the documentation, generates the documentation according to that. So if you use Sphinx, we will lose a lot of that, I think, unless we create basically a Rust plugin for Sphinx that is amazing. This is also like LXR. It will be possible soon to click on all these names to cross-reference things. You see the code directly in the documentation. You can jump out in and out of it. You can do search very quickly. I think it's client-side. Yes, it's client-side, so it's through JavaScript. So you can even do something like LXR or Boolean Elixir right in the documentation. The documentation looks like this. It's Markdown, basically, in the kernel code. And actually, these code samples, the examples in the documentation can be run, and can be compile tested at least. We could even runtime testing. So that's very nice. It's a very nice feature, I think. We have compilation working, of course. This will be like the if-defs or the ifs that we do in the preprocessor in the C side. So it's working. We have some very strict coding guidelines as well in the kernel. So as you can see here, I cannot extend myself much, but what we are trying to see is basically what we are trying to do is raise the bar on strictness, let's say, on the coding guidelines. So we are trying to, from the get-go, put very, very strict coding guidelines so that we don't have to do them later, basically. The abstractions will look like this. And I will leave that slide on while I read the question. Are there any reference kernel modules written in Rust available? Actual, some working driver. So we have some samples in the tree that we test in the CI. There is also Weston is working on the NVMe, and he can tell you more about that. on the NVMe driver. We also have the one that he posted as well on the GPIO example driver as well. And we hope to have more, of course. So yes, there is some actual working drivers already. No, thanks to you. This is how an implementation of the abstraction would look like. This is taken from the kernel tree, our fork, I mean. The driver code will look like this. If you want to know more, you can go to this article, which is the one I just referenced, which is basically how it will look. This is the C side. And for example, here you see that we are computing for the write B operation, the GPIO and TCPIO driver. We are computing some address manually in the caller side. And that's completely unsafe, of course, on Rust, because you cannot know what is, if you pass an arbitrary pointer to this function, then you're writing to any place in memory. Instead, what we do is provide functions that contain already the offset. So, well, in this case, that wasn't wrote here, what we are doing is passing an address, and this function knows at compile time, it's able to check that this is not outside of the region that this object knows about. So this object knows about the size of the region, and if you go try to call something outside, it will complain. But in general, we can even abstract this even more and have this already, instead of having a write B function, having a write, for example, GPIO IS, and then we don't even have to have this parameter here. Testing code will look like this. We can discuss how it can improve. Right now, we are testing this only on the host, but I want to work on this soon. So the idea is to have tests like native Rust tests and have them even working like key unit or self-test. So for example, at boot time, we can test this. So we could put an attribute here that says this test should be run at boot time, for example, and that would be automatically picked up. And that's the only thing you need to do to add a test to the kernel. Yeah, I want to skip that. And basically, I wanted to have some discussion on how to proceed from here, because the big question, and I hope during, well, in these minutes or the next, in the next days, we perhaps have a slot for discussion on this. It would be really nice if the organizers allow us to have an unconference slot, as I read in the webpage. So how to proceed? Because there is two questions. One, do we want Rust?
Before our keynote starts at the top of the hour, which will be Mad Dog. So if we could maybe wrap up in about 5 minutes, and there will be plenty of hack rooms, or maybe we can schedule a BOF on Friday. So those might be the options if we want to do a follow-up discussion. Perfect.
Yeah, this is the last. This is the last slide, basically. So yeah, the question is in the what we would like to discuss with you and kernel maintainers and developers in particular is how do we proceed? Because for example, if you want to do, you're a kernel maintainer, you may be okay with Rust, but the problem is other kernel maintainers are telling us, yes, but I do TD-wide changes, or I do subsystem-wide changes sometimes, or I work on a driver, but I need to add a new feature to your subsystem. If your subsystem is using Rust, now I have to learn Rust. And that's a completely valid question, and we have to find a way to make it as easy as possible for kernel maintainers and other developers to have probably a transition period where we help them to maintain this code. But eventually, we want to have Rust as a first-class language in the kernel, because otherwise it's impossible. It's impossible that we have a set of people working on the Rust side and a set of people working on the C side are completely separate. But ideally, the goal is that kernel maintainers accept Rust code in their subsystem, and that's and as soon as they do that, when somebody needs help, either us or the kernel maintainers, as soon as somebody needs help from the outside to modify that Rust abstractions, those Rust abstractions, we will provide help. But we could do this, for example, for 1 year or 2 years or something like that. But then eventually what we need is that the kernel maintainers and the developers are able to read and write Rust code. And I think that's unavoidable. If we put Rust in the kernel, we should do it as a first-class language. If we are going to do it like in a corner, I don't think that will work too well. Let me catch up with we have 3 minutes left. You think we need a set of Rust maintainers first? I can learn language for the drivers. I need to. Yes, exactly. That's the question we want to see. So we have discussed of having Rust maintainers and having a set of people that can help basically anywhere in the kernel with the Rust instructions. But in the end, we need people to get to learn Rust. We cannot continue basically forever with that. That will be the problem. Yeah. So if there is any questions, sorry that I had to rush the presentation. It's a lot of things to explain. It's a lot of content to basically say why we want Rust in the kernel and why there's a lot of points to discuss. So yeah, I wanted to make it as quick as possible, have discussion, but I understand that we will do it through the week. And if you are a kernel maintainer, let me just say, if you are a kernel maintainer, you are interested in Rust, or at least you want to learn more about it, please contact us, sorry, because we want to have, well, the first kernel maintainers. We have, for example, GPIO guys, folks are on board with us, and they said, okay, let's try. We want to have more people that is willing to give it a try on their subsystem. So we need some users to put this in the kernel, and it's a bit of a chicken egg problem. To put this in the kernel, we need some users first, and to have some users, we need, yeah. So thank you everyone for coming, and thank you for having me here. That's the link of the project, and yeah, hopefully you can reach to us and discuss on, especially if you are against the project, please reach out and try to discuss, and we need to see how we are going to make this, how we can make this happen if the majority of people want Rust in the kernel. Thank you.
All right, thanks, Miguel. So this wraps up the first day of the Kernel Summit track. As I mentioned earlier, we will be taking all of the notes and adding them to the Google Doc so we can have an archive of the shared notes. The keynote is going to be starting in 5 minutes. Note that we're running into some scaling issues just simply because the LPC has been so popular this year. If you have trouble joining the BBB room for the keynote, since everybody at the LPC will be joining the keynote track, please, if you have trouble there, you can use the YouTube live stream, which will be available. The live stream URL will be the LPC referee track, and you should be able to find that from the LPC website. Find the free YouTube live stream link. So if you have trouble accessing BBB, an option is to try using the YouTube live stream. Thanks again for bearing with us for some of the technical difficulties we've had on this first day. Again, I want to reiterate my great thanks to the LPC Planning Committee for all of their hard work in putting this together, and all of the sponsors for the Linux Plumbers Conference, without which obviously this event would not be able to happen. Thanks all. Martin, did you want to ask a question?